chaotic model in quantum physics. Welcome. Please start recording.
Great, okay. Let me share my screen. So it'll be a Blackboard style talk. But people should see now a whiteboard. It's working okay?
Yes.
Perfect, okay. Great. So welcome everybody. I'm happy to be here after several years. I don't remember which, I think this course was originally planned for 2020. So it's, I'm glad that after all of these years, we've finally managed to get together. So what I'd like to do when Wilson invited me to give this course, I think if I remember correctly, it was several years ago now, but the suggestion was to give a course on p-adics in physics, and more or less the format and the exact content was sort of up to me. And so I've given it some thought. I think probably what I'll end up doing is I'll try to give sort of a very leisurely, slow-paced introductory overview of both some areas where the p-adics are applied to physics that I've thought about a little bit in my own work, and also some areas which have to do with other people's work, but which I think are interesting. And I'd like to sort of maybe give an idea about like where you might hope to profitably change the field of numbers that appears in a given physical model, and what you might hope to get out of that in each given example, where you could expect it to succeed, and what sorts of new features or new behaviors you could expect to get from it in each case. So yeah, I'd like to keep the tone very informal. And I mean, this is really a student event, right? So people should feel free to stop and interrupt and to ask questions. Is there a way for people in the seminar room to ask questions easily? I mean, if it's easier from the format, people can ask at the end or whatever works. But if people have questions, please don't hesitate to stop me, or if I'm moving too fast. I guess I've made a few choices, I guess, about what to cover and what not to cover. So let me start by giving a little bit of an overview with that. I'll begin by trying to give sort of an abstract setup for some broad class of physical models. And I certainly don't want to claim that this class contains every physical model that you might be interested in, but I would like to sort of set it up in such a way that it encompasses most of the models people tend to think about. So it should include things of the following type. It should in particular include things like field theories. This is something that's kind of a main focus of interest for me. But I also want it to contain things like spin systems. And other discrete models, like things like the Ising model.
Well, it would be possible to have a bigger phone. Would you please increase the size of the phone?
Let me try.
Because due to the COVID restrictions, Okay, perfect. Thank you very much.
So people are far back, I see.
Yes.
So it's better like this? I'll try to write large.
Yes, perfect. Thank you.
Great. And I guess it should, let's see. I'd also like it to include first quantized models. What do I mean by first quantized model? I mean something like string theory or single particle quantum mechanics. And what's important to remark on in this case is that the models will be similar. For example, often when we talk about worldsheet string theory, we're really talking about a particular two-dimensional quantum field theory, but the interpretation is quite different. And it should include other things, but maybe not everything. So after having given that sort of broad setup, I'd like to discuss where fields of numbers and other algebraic structures appear in that formalism. When I say a field of numbers, I just mean the object that's mathematically called a field. I want to refer to it as a field of numbers just so that people aren't confused, because when I say field theory, that usage of the word field is quite different, unfortunately. So where fields of numbers appear in models of this class, and what roles they play. Or what structures are important. So one big lesson or one big theme, I think, in mathematical lines of research is that it's important to sort of abstract question. It's okay. It's important to sort of think about a given model and not think of it as just a particular concrete thing that you can do, but to ask, what structure is important to do the calculations that I want to do? What's the sort of broadest generality in which I could set up a model of this type? What structures are essential and what structures are inessential? And this is something which happens a lot with highly structured objects. So just as a side remark, highly structured objects are rich. You can do many, many different things with them, but they're also confusing. They're confusing because I have many different ways to think about them and many different independent pieces of structure to use that may sort of coincide in that special case. So to give a couple of examples of what I mean by this sort of piece of philosophy, Riemann surfaces. Are an example that shows up a lot in physics. A Riemann surface could be a one-dimensional complex manifold. But it could also be a two-dimensional surface. Real surface. With a conformal class of metrics. And it could also be an algebraic curve. So a so in principle, these are three totally different kinds of objects. And I can generalize them all in very different ways. For example, I could ask about d-dimensional complex manifolds. That's totally well defined. But not every d-dimensional complex manifold will be a projective algebraic variety of dimension d, although the implication is true in the other way. And it gets even worse if I think about a 2D dimensional real manifold, smooth manifold, equipped with a conformal class of metrics. In higher dimensions, that has nothing to do with complex geometry at all. So these are three different things which are sort of very different types of structure, which precisely in the example of a Riemann surface are all equivalent. But not generally. So that's a sense in which it's confusing. If you have a computation that works for Riemann surfaces, sometimes it's a little bit hard to know whether that computation is really telling you something about conformal geometry or about complex geometry or about algebraic geometry, because for Riemann surfaces, there's often a version of the proof for each type of structure, for each way of looking at a Riemann surface. Whereas in general dimension, maybe it generalizes nicely for one of these pictures. It's a story about, for example, polymorphic geometry, but there's no good conformal analog in dimension 16. That can and does happen. But it's also in a sense rich because precisely for the same reason, I do have many equivalent pictures of the same phenomenon. And as an example of an application of this, you can sort of imagine that the fact that p-adic string theory is around. Or several other things that appear in the context of low-dimensional field theory. They sort of use the fact that a priori in string theory, maybe I'm interested in a conformal class of metrics. I've wanted to write down some sigma model to a Riemannian space. And I'm interested in, for example, doing a path integral over various embedded surfaces. which somehow admits a symmetry by conformal rescalings. And in doing that path integral, I find that there are ways of reformulating it that allow me to imagine integrating over the moduli space of complex structures on the Riemann surface, because that's the same as the moduli space of conformal structures. And in fact, there are sort of algebraic, even more rigid versions of the whole story where I could imagine the string worldsheet as really just being an algebraic curve. So that's a sense in which I have many more tools to do two-dimensional field theory than I do to have other than I have to do other kinds of field theory, precisely because I have pictures of what's going on in two-dimensional field theory that refer to algebraic geometry in kind of an intrinsic way. So let me give another example. Another example is the field R. R is in a sense a very highly structured object, and you might imagine that different pieces of its structure are important for different purposes. So for example, it's a field, so it has lots of algebraic operations. It's also a topological space. So it has sorts of notions of continuity. It's a normed field. And it's normed in a way that's compatible with the topology. So it has sort of notions of distance. What else is it? It's totally ordered. This is in a sense maybe the most surprising property of R, or we use this all the time, right? We use this for comparison or size estimates. We use it to define inequalities. But in a sense, it's the total ordering that's maybe one of the most rigid properties on R. I think if you ask for total ordering together with norm completeness, then maybe R is the unique example of such a field, at least in characteristic 0. So let me write norm complete. This means that it has, in a precise sense, no holes. That precise sense means that all Cauchy sequences converge. Et cetera, et cetera, et cetera. There are probably many others. So, I mean, what could fall under, et cetera? I guess I could talk about things. I mean, you've had a course, I guess, on things like the Haar measure, the Fourier transform, other notions of additive and multiplicative characters. There are lots of structures that I could start defining. And again, when you are used to constructions involving the field R, it's helpful to think which of these properties are really the important properties in my context. Which of them do I need and which of them do I not need? For example, do I need the fact that it's a field? Often in physics, we use R as sort of a local model for topological spaces like manifolds. And then we don't really use the algebraic operations at all. We just think of R, or the Cartesian product of n copies of R, as a model of a nice topological space with sort of a normal notion of continuity. And then I glue together other spaces out of patches like that, so that I have a good notion of what it means for functions to be smooth. I can take derivatives, for example, of functions on such a space. And it's only a little bit that being a field creeps in. I mean, it sort of creeps in a sense, through the definition of derivative on Rn, but nowhere else. And if you think about this for a while, you sort of notice that total ordering is very important in some places and not at all in others. This is maybe the strangest. Or sort of least generic. Property of R. And in a sense, one starting point for questions about p-adic mathematical physics is just to ask, when do I actually need the total order? And when can I choose some other field that has all of these good properties? It's not totally ordered anymore. But if I choose another local field, for example, QP, it will have all the algebraic operations, it will have a good structure, it will have a good topology. It's a very different topology, but it has a good topology coming from a norm. That norm gives me a notion of distance, which plays in a counterintuitive way with the algebraic operations, but it's a perfectly well-behaved notion of distance. It's norm complete with respect to that notion of distance. I have Haar measures, I have Fourier theory, I have characters. And so in a sense, when I work over non-Archimedean local fields, I've given up one piece of structure in exchange maybe for other pieces of structure. So let me, just to keep track of this here, let me say. I give up on total ordering. They'll have more or less similar packages of structures on them. And that means that I have a natural generalization that preserves all of these structures but one. And in particular, as you will know very well, there are local fields of the form QP, but there are also function fields. And then there are extensions of these. And in exchange, I get other structures. One of these is a discrete valuation. That means that the norm actually doesn't take continuously many values. They're actually just, as a topological space, discrete values for the norm that divide my field into sort of, you can think of them as being like annuli, where each annulus consists of a collection of elements that all have the same length, all have the same norm. And there are countably many such families. And topologically, they're totally disconnected from one another. This is sometimes useful because it means that things that in the real case would be integrals, often in the p-adic case and the non-Archimedean case, are sums. I also get an ultra triangle inequality. And this means that many things about triangles behave better. For example, all triangles are isosceles. This is something that I'm sure people will have seen before, so let me not go into detail about it. The sort of general point I'm trying to make is that in looking at a package of structures that you might have on some object that you've used repeatedly in lots of examples that you like, there are lots of physical models that make use of R in various different places. You might ask, which structures am I actually using in any given appearance of that object? And which ones could I not ask for? And then if I stop asking for one of them, I might ask, what's the class of objects that has all of the structures I need, which behave in the ways that I want, but where I don't have that extra structure that wasn't important anyway? And then I sort of get a natural family of generalizations of my model where the object that appears in that position has all the structures it needs to have, but no superfluous ones. And that's sort of a useful, it's really a useful way of thinking, not just in the example of the p-adics, but in any sort of example where you have a model that's of special interest. I would argue that it's always a good technique to ask, what structurally is happening? What's the most general possible formulation of this model? So a lot of what we're going to discuss in the next large number of hours, I think I have something like 6 hours, although I'll probably end in time to give a slight break before the conference session starts tomorrow. I'd like to give sort of this general formulation of what a wide class of physical models look like and where they actually use number fields, where it's important to take things to sit in number fields. I should be careful again about terminology. So a number field is strictly speaking a finite extension of the rational numbers. I don't mean that. I mean a field of numbers in the sense just a field. Sorry. Yeah, so I'd like to sort of draw a map of where fields of numbers play a role in the formulation of a typical physical theory of this class that I'm interested in. I'd like to give some comments on where you might hope to profitably change the field of numbers or abstract away from using a specific field of numbers at all. Rather consider, for example, all fields at the same time. It's an important idea. Then I'd like to discuss some models in detail. And I think one of the things I'd like to maybe focus on a bit is related to this idea of the discrete valuation. The fact that scale transformations in theories that are defined over the p-adics are often better behaved than scale transformations in normal quantum field theories. And so in particular, that means that there's a really nice theory of renormalization group effects in a wide family of p-adic quantum field theories of a particular type. And it's precisely that fact that the scale is, in a sense, discrete, that's responsible for certain phenomena also in holography. So the way I came to thinking about the p-adics was in the context of trying to make discrete analogs of the ADS-CFT correspondence. And a way you can think about the ADS-CFT correspondence is more or less a way of taking a given quantum field theory and spreading it out. So you start with a field theory in d dimensions. So let me call this a side remark. So roughly, and this is just going to be sort of preliminary remarks that I'll come back to later. Holography works by taking a d-dimensional quantum field theory and spreading it out into d+1 dimensions. Where the extra dimension plays the role of a scale. So you can imagine a picture like this. Here's my d-dimensional quantum field theory. And I add this extra direction. And that means that that new coordinate is telling me that if I'm thinking about theories at different points, those are actually sort of the same theory, but viewed at different scales, meaning that I've integrated out high energy degrees of freedom. So this is like my theory in the ultraviolet. And as I go up and up and up, I integrate out more and more of the effective degrees of freedom of this theory. That means that I change, for example, the coupling constants in some well-defined way. And going deeper into the bulk is like going into the infrared. That's the sense in which the extra dimension is like a scale. And the geometry is in some sense hyperbolic. Let me write hyperbolic-ish for now, because the way I want to argue this is that as I integrate out degrees of freedom, I haven't really said yet at all why this is a sensible procedure. But you can imagine that as I do this, I lose degrees of freedom, and I do it in an exponential fashion. So if the degrees of freedom here look like they're on a lattice, and that lattice has some characteristic spacing. What I do when I go to the infrared is I'm supposed to integrate out high frequency modes. The high frequency modes will be one in which neighboring degrees of freedom are not correlated at all. And effectively, I can think about that as grouping blocks of degrees of freedom and averaging over them and sort of writing a smaller number of effective degrees of freedom. So here I may have a grid whose spacing looks quite a bit wider, and here even larger still. And if I imagine the sort of metric on my space as being defined by the number of degrees of freedom per fixed volume, the number of degrees of freedom per box is getting smaller as I go up because I've integrated out degrees of freedom. And it's getting smaller exponentially because every time I block, I sort of lose half of my degrees of freedom. That's the way I can think of it. And so that means metric at least thinking roughly in terms of degrees of freedom, scales somehow inversely with the new coordinate. And I'm totally not being precise here. You shouldn't expect this to be precise, but what I want to do is give sort of a flavor for why you might imagine if I just took a random d-dimensional theory and I thought about spreading out its renormalization group scale into an extra dimension, why that extra dimension might sort of have an overall hyperbolic geometry. This might remind you of a few things. So I hope this will also remind you, for example, of the way that the p-adic distance function is constructed by using sort of a p-to-1 grouping as you go up in the scale coordinate. I'm going to return to that later on, but this reminds you of the p-adics. That's not at all an accident. And it's affected in certain examples. The boundary is conformal. And it's dual by this procedure. To a gravity theory. In d+1 dimensional hyperbolic space. And so the way ADS-CFT was found traditionally, you actually started with examples where this mysterious duality works perfectly, and those examples have really lots of extra structure. They involve supersymmetric field theories. They were constructed using string theory. The duality is exact. It works in some way where you argue using, for example, closed and open string states. I don't really want to talk about any of that way of arriving at this correspondence here. I'd just like to sort of fix in vague terms this idea that any quantum field theory comes with a scale because of the theory of the renormalization group. And I can sort of at least formally think about adding an extra coordinate, which makes that scale look geometric. And what the ADS-CFT correspondence tells me is that at least in some particular examples, that's a sensible thing to do. And it lets me do computations in a higher dimensional theory and duplicate computations in a lower dimensional theory. So that means that the scale can actually be made geometric, not just in a formal way, but in a meaningful way. And so just to complete this side remark, which is going a bit long, the reason that I originally became interested in the p-adic numbers in physics is sort of because of the observation that if you think about just doing this thing, which people did in papers from really a long time ago, at the time when the renormalization group was being developed, and you just imagine averaging over collections of neighboring degrees of freedom. So for example, the 4 guys which are in this block, they're just averaged down to 1 degree of freedom here, and so on and so forth. That sort of hierarchical structure is, in a sense, closely related to p-adic norms, and much more closely related to p-adic norms than to the normal Archimedean story about scale.
Sorry, Igman, it seems that we are not seeing that you are writing.
Okay. So it's not scrolling if I do this?
Yes.
Okay, maybe I'll go to the bottom. This is where I want to be now.
Thank you.
It looks like it's up to date now. Okay.
Yes.
Great. Are there questions at this moment in time? So this, I guess most of this is by way of overview.
Igmar,
yeah.
Could you please comment? I mean, I think it's good that you emphasize the order in the numeric line. Could you please comment about causality in physics and connections with the order over the real line? I mean, probably you're going to discuss this later.
Right. So this is a sort of deep way in which we use the order, I guess, on R, is when we talk about the arrow of time. And we say that one event is after another event. And I don't know that I have a really good comment to make about this. So, I mean, there's sort of the immediate comment you could make, which is that already when we talk about, question, which is a very good question. Causality depends on ordering. Right. So if we want to think about I'll make a couple of scattered remarks. I don't think I have anything really good to say about this. So in the Galilean world, time is absolute. We only allow Galilean transformations of the space-time, and it's meaningful for events to be simultaneous. And so that means that events are totally ordered. Well, up to simultaneity, I guess they're totally ordered. It's enough to say that they're totally ordered. So there are no coordinate transformations in the Galilean world that mix space and time. And so my space-time is really space times time. R3 times R. And the only transformations that I allow are sort of shear transformations. by a given velocity and rotations of R3 and translations in time. And all of those preserve the total order of events. So if an event is a point in this space-time, we can say that an event takes place at a point in space-time, right? So xt is before x prime t prime if t is before t prime. And this relation is preserved by the Galilean group. In special relativity, it's already a little weirder. So there we say that space-time, now it's a genuine space-time. It's R3, 1, and it's acted on by the Lorentz group. And the Lorentz group does not preserve the time coordinate or just act on it by shifting. It does much weirder things to it and can mix it with spatial coordinates. So what's the right notion of causality in relativity theory? We would say that xt is before x prime t prime if the Lorentz norm of x minus x prime, t minus t prime is time-like, and the distance in time is positive. And this is not a total order. So, I mean, in a sense, I guess the comment that I want to make by saying this is that already in a special relativistic theory, if you think about events, you've already given up on the notion of having a total order on events. You just have a partial order, which is compatible with the symmetries that you have. And so I guess maybe the right way to formulate the question, for example, in some p-adic model or a model where you don't really have the real numbers around to impose a condition like this one or this one, is to ask, are there consistent partial orderings on events? And do those make physical sense? I don't think I know a great way to do that in examples. So this is maybe more of a random comment than a good answer to your question. But I think it's certainly not, it wouldn't exclude a physical theory to say that the events can't be totally ordered, right? Because even in the theories we know and love, they can only be partially ordered. Of course, it happens that we build that partial order by using a total order on the time coordinate or on the norms of the 4-vector coordinates. But you could imagine that maybe there are other ways of putting interesting partial orders on the space of events. Maybe even so that that partial order wouldn't come from a total order.
Thank you, Igor.
Thanks for the question. Are there other questions at this point?
No.
Okay, great. Okay, so we're, I guess, nearing the end of the first hour, which means that most of what I've done has just been sort of introductory. I hope that's okay for people. I think the pace will pick up a little bit in the next few periods of time. So what I'd like to do with the last few minutes is maybe just let me start building a version of this sort of schematic class of physical models that I'll be interested in. And I'll try to sort of justify at every step why this is reasonable, and maybe talk about why models you may have seen fit into something of this sort. But I'm intentionally going to talk about it in a little bit of a vague way. And I just want to mention that the problem of trying to axiomatize what information you really need for a physical theory. Lots of people have made very, very intelligent attempts to do this, and all of those attempts are probably better than what I'll try to do here. I'm giving you, in a sense, just a very hand-wavy approach to how you might think about the ways in which many related physical models sort of fit together from the perspective of someone who thinks about field theory a lot. So it's clearly a biased perspective. So I'd like to sort of imagine that there are two basic kinds of objects. Parameters and degrees of freedom. And I sort of want to distinguish these by saying a degree of freedom is something that has dynamics. I want to somehow, depending on what I mean by dynamics, describe what the degrees of freedom do. The parameters don't have dynamics. They sort of label the degrees of freedom in a way that's maybe interesting. I'm going to call the space of parameters sigma, some object. The degrees of freedom are going to be labeled by something called X. It's again some object, maybe a space or maybe a set. And I want to think about a history of the system. As a map. In other words, an element of this space of maps. So, for example, what would be some things you could do? Sigma could be the time. And if I were doing quantum mechanics, I could imagine that my degrees of freedom are the positions and momenta, or the generalized coordinates and generalized momenta of some system, which I want to quantize. A history of the system is a bunch of functions, namely the generalized coordinates as functions of time and the generalized momenta as functions of time. So what am I building up? I'm saying example in classical mechanics. At least the classical mechanics of a particle. Sigma is the time. X is the phase space. And or possibly the space of coordinates. And I want to remain a little bit agnostic about this because, in fact, it'll depend if I'm working in a first or second order formalism, whether I want to think of X and P as independent degrees of freedom that are related by Hamilton's equations, which are first order, or whether I want to think about a history as being just a single function X of T, which obeys a second order differential equation. So even the space X, right, there might be many ways of setting up the space X to describe the same system, which are different. And the first and second order formulations of various theories are going to be examples of different choices of this data for the same theory. There should be observables. What should observables be? The observables are going to be appropriate functions from histories. To numbers. And roughly speaking, what that means is that a measurement that I make is some kind of number, and that number should depend on what state the system is in, what it's doing over time. And you'll remember that in classical mechanics, the algebra of observables is precisely the algebra of functions on the phase space. So I think we're actually out of time for the first hour. So maybe this is a good moment to sort of leave it and take a break, and then we'll come back at, I guess, your 11 a.m., my 6 p.m.
Yes. Are there comments or questions? Okay. Thank you, Idmar.
Thank you so much. Yeah, we'll see you soon.
Okay. Thank you. Bye. I'm sorry. I'm sorry. I forgot to the speaker. Let's start to the speaker. So, see you in.
Yeah, we'll see you guys soon. I can just leave this running, or I don't know what's best.
Excuse me?
Shall I leave the Zoom running? I can just mute the sound. Or
no, don't worry. You can close your session.
Yeah, okay. So then we'll see you in half an hour, yeah?
Yes.
Great.
We have 30 minutes. So, okay, now we have the second part of the course by Professor Sabel. Please, continue.
Great. Okay, thank you. Let me share one more time, and I'll just pick up where I left off, I guess. Great. Okay. So welcome back, everybody. So just at the very end of the first hour, I was starting to talk about a sketch of how I like to think about a general sort of class of physical models that includes most field theories and also some other things. And the basic way we set up this sort of class of systems was by writing down a space of maps. It's the space of maps from some space that I think of as a parameter space called sigma, to some space of degrees of freedom, which I called X. And I sort of want to distinguish between these two things by saying that in the theory I'm thinking about, the degrees of freedom are going to have dynamics, obey equations of motion, and so on. The parameters are just going to label where those degrees of freedom are, or the fact that they're associated maybe to points in time or to points in space. So in a sense, a degree of freedom is like a measurement that I could make, or a dynamical quantity that I could measure. A parameter is like something that labels the family of things I could measure. And I want to emphasize that it's a little bit subtle which it's a little bit subtle, for example, where space and time should go in this setup, and there are different options. So space of histories. Maybe I'll denote that with the letter E. That's the space of maps from sigma to X. And I haven't yet said what kind of objects these are. For now, you can think about them as being sets. They'll have much more structure than sets in general. And one should note that it's unclear to sit specifically in either, it's not necessary for space and time to sit specifically in either sigma or X. For example, in classical mechanics, sigma is time. but X is space. This means that we write down coordinates of a particle for a particle, let's say. This means that we write down coordinates xi of t. That's saying that we have coordinate functions of the time and they evolve in time, and we solve for the dynamics of the coordinates of that particle. And the space where we live has coordinates, which are the coordinates of x. On the other hand, if we think about a field theory, then we really think about sigma as being space-time. And X is sort of really the space of fields. And that's just some sort of auxiliary vector space. For example, in a theory of one scalar field, we would say that X is the real numbers or the complex numbers. So here we would think about fields of the form phi of t and x. In string theory, we do something totally different. Analogous to how we think about a particle moving in space, here we actually think about sigma being the world sheet of the string, and x as being space-time. So people tend to write this in the context of string theory by saying that there are coordinates on space-time that parameterize an embedding of the world sheet. Those look like coordinate functions x mu that depend on world sheet coordinates tau and sigma. And so I just want to emphasize a bit that where you think you are living, or what you regard as being the coordinates of the geometric space and time where you sit, it depends very much on the way your theory is set up. So sometimes people will call this second quantization. And this first quantization. Although I want to emphasize that there's really nothing that I've said is quantum at all yet. I haven't quantized. I'm just describing the classical way in which the degrees of freedom of the theory are being described. But nevertheless, it's true in each of these cases that there's a way of thinking about my degrees of freedom, this space E, as a space of maps. What other sort of information do I need? Well, I have sort of observables. And here's the first time where some algebraic structure is kind of going to be automatic. There's actually going to be an algebra structure on my observables. I want to think of an observable as being a function from histories, so from E, functions on the space E that are valued in K, where K is some space of numbers. Where I imagine my measurements taking values. The observables don't necessarily have to be all functions. They might, for example, be continuous or well-behaved functions, or smooth functions, or measurable functions. Typically, there will be some conditions on what space I'm interested in here. But nevertheless, it's going to be a function of some kind from histories of the system to numbers. And one other remark I'd like to make in this context is that these are really off-shell. Observables. So there are no dynamics at all yet. We're doing sort of a purely kinematic. Setup of what the space of fields is. What other sorts of things should I imagine this giving me? Well, this actually gives me a notion of the classical, Boolean algebra of statements. About my system. So a statement for me is going to mean something that's true or false about the system, which is experimentally verifiable. You should think of, for example, if U is a subset of K, and F is an observable, I can ask, is the value of F in U? And that's a yes or no statement about the system. And that corresponds to a subset, F inverse of U, which is some subset of the histories, namely the histories that are compatible with that yes or no statement. And another remark I want to make is that there are theorems. For example, there's a theorem called Stone's Reconstruction theorem, and there's a generalization of this by Loomis and Sikorsky. That reconstruct the space E from the data of its Boolean algebra of subsets or its sigma algebra of appropriate subsets. So there's a whole sort of direction of research that has to do with understanding classical theories in terms of the statement of all possible true or false, the collection of all possible true or false statements about such a system, and implications between those true and false statements. And because classical systems work according to classical logic, what you get from the sort of totality of all yes and no statements, all sort of Boolean things that you could say about a given system, is some Boolean algebra. Boolean means that there's a notion of the value of f not being in U, so there's a complement. And there's sort of a partial ordering, which comes from containment, which says that one yes or no statement implies another yes or no statement. And I'm not going to be too careful about the whole logical formalism here. But the point is that assuming that the things I can measure come from the functions on a space, or the subsets that are obtained as like pre-images under observables in some space E, it's not actually assuming very much about the system because of reconstruction theorems like this. Those say that if I have some physical system and I know all possible statements about it, binary statements, and the whole logic of implications between them, it's actually sufficient to know what to reconstruct the space E. And I just want to make this remark because this is a thing which in the quantum mechanical case has an interesting generalization that I want to come to in a minute. The fact that E is a mapping space is not something that you get. So these theorems allow you to reconstruct the space E of histories, for example, or maybe Anschaull histories. They don't necessarily allow you to write that as a map between two spaces in an interesting way. That's something that is more for me associated to the class of field theories, the class of theories that one tends to like to write down in examples. And there are many similar notions of reconstruction. Let's see. Yes, Hobbes. A space E from a commutative algebra of classical observables. So for example, there's a construction called the spectrum. This is common in, for example, algebraic geometry, but there are versions that are defined for C-star algebras, which are more appropriate for quantum theory. So to talk about the spectrum, we let A be any commutative ring. And then we build a space spec A from it. Spec A is defined to be the set of equivalence classes of maps. So here, rho is a ring map. And K is any field. What does the equivalence mean? Well, rho is equivalent to rho prime if the following diagram commutes. I have one point in spec A, which is rho, mapping to a field K. And then I have another candidate point, which is a ring map rho prime mapping to some other field K prime. If there's a map of fields like this, which makes this diagram commute, then I should regard rho as being equivalent to rho prime. So I'm sort of interested in maps from this ring to a field, which do not just arise by extending scalars after mapping along the same map. And it turns out that this defines an equivalence relation on ring maps from A to a field. And in fact, you can put a topology on the space of all such maps. So spec A is a topological space in a natural way. And A is the functions on spec A. Spec A is in fact a ringed space, and A itself is the functions on it. So examples. This is a construction that's familiar from algebraic geometry, perhaps if people have seen it there. This is the way in which you go back and forth between the algebra functions on an algebraic variety and the variety itself viewed as like a topological space. But normally the way people define it is they talk about the set of prime ideals in A. And to me, it's sort of much more interesting and transparent to think about it in terms of equivalence classes of such maps. Because if you like, this is really saying, what are all the possible notions of expectation value that I could have for an observable? So the way we defined observables above is we sort of define them to be functions on E with reference to a fixed field. But you could imagine a more general notion of observable, which just has an algebraic structure coming from somewhere. And what this is sort of telling us is that the space E, which is constructed so that observables A will be functions on that space, can be thought of as the space of all possible ways of mapping an observable to a number, where that number is totally abstract. It's an element of any field. So let me give an example, because I think sometimes this is a little counterintuitive. And it's something that actually does come up quite a bit, like this intuition in the context of a lot of work in modern field theory, topological field theories especially. This kind of thinking it ends up being essential. And you often define the moduli space of a given field theory, this object E, as being the spectrum of its algebra of observables, which you can compute in some more algebraic way. So I want to go through this example in just a little bit of detail to sort of emphasize that already when we think in this way, we're sort of implicitly being agnostic about the space of all fields, at least implicitly. So here's an example. Let's think about the complex numbers with one variable adjoint. So this is a polynomial ring. And you might say, well, that looks a lot like the functions on C, right? If X is a linear coordinate on the space C, then this looks a lot like functions on the line. In fact, you'd be right, but let's sort of see how it goes. If I want to write a map of this to a field, one way to do it is to take the quotient by an irreducible polynomial. But because I'm over the complex numbers, all the irreducible polynomials are linear. So I could do the following thing. I could map Cx to C by the map that sends x to alpha for some alpha in C. And that's a map from this ring to a field. It's a ring map. And this is the prime ideal generated by x minus alpha. So that's already sort of giving you the idea that maybe spec of Cx is C. But there's one more point. Namely, I could take polynomials and I could think of them as a subspace of the field of rational functions. So if you like, this is the prime ideal 0. In algebraic geometry, this is called the generic point. You might wonder if there's a way of distinguishing. We can sort of between normal and strange points. By asking for surjective maps. That means, I guess, that we're really asking for maximal ideals, not prime ideals. I think that's the condition. Those are a subset of the prime ideals. Let's do another one, just real quick. So if we took Rx, there are going to be actually several different classes of points here. So there's going to be the point that sends Rx to R by just sending x to a number. It's a normal point. But there are irreducible polynomials that are not linear over R. In particular, there are quadratic ones. So we could divide out by the ideal generated by the quadratic polynomial x squared plus a. And that maps to the complex numbers. And that's a perfectly valid point, according to this scheme. And then, of course, there's also the point that takes Rx and includes it into rational functions with real coefficients. So this is sort of the phenomenon that you can see points over an algebraic closure. These are the sort of normal real points. And this is this weird generic point again. The point is that there's a very good theory of spaces These are sometimes called affine schemes. And if you haven't heard this term before, you shouldn't be scared, because an affine scheme is the same thing as a commutative ring. In fact, the category of affine schemes is the category of these things is by definition the category of commutative rings, but the opposite category. That means that if I have a map of rings from R1 to R2, it defines a map of schemes going from spec of R2 to spec of R1. And that's saying that, for example, if I have a subspace of a space, then the functions on that subspace are a quotient of all of the functions, namely by the ideal of functions which vanish along that subspace. So we can also implicitly define the space E by saying my algebra of observables is some commutative ring and then I'm sort of forced to say that E is the spectrum of my commutative ring. And this is actually a common approach. So this generalization doesn't specifically have to do with a non-Archimedean field, but I really want to emphasize that this is something which is done frequently in the physics literature, at least in certain corners of it. When people think about studying, for example, twists of particular field theories, they often compute the algebra of observables using sort of very much algebraic techniques, and then study the object, which is the spectrum of that ring, which is some kind of moduli space of solutions to the equations of motion of the theory. And it's quite common to go back and forth in this way. And the other reason I want to mention it is that there's interesting work that I might like to comment on at the end if I have time. By Min-Hyun Kim and collaborators. That uses the idea of attempting to study field theories where the algebra of observables is some arithmetic object. For example, the integers. And this is a direction of generalization which is, I think, distinct from the one which is normally done in constructing p-adic models. As we'll see in just a moment, the typical p-adic models make a more moderate alteration. So for example, they would say E is still a space of maps from sigma to X. But for example, sigma is now a p-adic space. X is maybe still a real space. Or perhaps both sigma and X are p-adic spaces. But the algebra of observables is the algebra of complex functions on that p-adic mapping space. It's a thing you could imagine doing. This is, in a sense, one of the most radical departures you could imagine making. But it's led to some interesting results, which are more or less in number theory, which I think should be better appreciated. So for example, there's a sense in which the spectrum of the integers is an object that's very much like a three-manifold. If you compute appropriate cohomology theories or whatever, you find strong analogies between the integers, spec of the integers and three-manifolds, and primes, and one-dimensional submanifolds of that three-manifold. And those one-dimensional submanifolds of three-dimensional manifolds you can think of as being like knots. And then there are interesting sort of completely arithmetic versions of, for example, Chern-Simons theory that people have tried to construct, where the whole notion of space-time is quite abstract. I define it by giving the algebra of observables, and the algebra of observables is just some interesting commutative ring that perhaps I'm interested in for other reasons. And there's a sense in which L functions and objects like p-adic zeta functions appear really naturally in this context. So I hope that if I have time at the end, I'll maybe get back to saying another word about this. But I wanted to have defined the spectrum because I think this is something that often goes missing in the modern, in the sort of textbook things that you learn as a physics student. Okay. Perhaps I'll ask if there are questions about that.
Are there questions? Igmar?
Gauss linking number. So this is like the expectation value of a product of Wilson lines in a Boolean Chern-Simons theory. And it's shown to be the Legendre symbol. Context. So sort of natural objects in arithmetic show up. You can sort of reinterpret them in this story in nice ways. And there's, I'd also look at this, these Kim et al. Papers. So they, construct sort of various objects. So they construct an sort of arithmetic Chern-Simons invariant. And compute various sort of arithmetically interesting objects as path integrals. Yeah, so I can give references to these papers because I think they're really worth looking at, and it's far enough outside of my daily bread that I don't think I understand them super well, but I do think it's worth trying to sort of build a bridge to them here and show how they fit into sort of this general picture of where you might try to find arithmetic generalizations for physical stories. Because this is a pretty natural one, I think. So I should say that also, so things like p-adic Gall functions come up in this context. And zetas, and so on. So it's quite tantalizing.
Thank you. Thank you. There is another question.
Yeah.
Hi, sorry. I had a concrete question about your definition of spectrum or ring. I was curious because I was not familiar with this description in terms of functions from the ring into a field. Concretely, I was wondering why you need to introduce an equivalence relation through this map you drew and you needed to commute. Because I think I've seen this idea in the context of the Gelfand transform. You take some map, a character, and then you take its kernel, and then you argue directly without equivalence relations. And this is why I was curious. Yeah, thank you.
Yeah, so you're of course correct. It goes exactly along those lines. So if I have a point rho from A to K, then the kernel of rho is a prime ideal of A. And of course, if I have equivalent maps, because every map between fields is injective, the whole equivalence class has the same kernel. And in fact, you can sort of find a unique representative by the sort of smallest representative. Is the one that sends A to A modulo kernel rho, and then you send that to the field of fractions. So the equivalence relation is, in a sense, not necessary. The reason I find it interesting to define it in this way is that it's sort of maybe non-obvious to think about what a prime ideal means from the physics perspective. It's at least not a thing you tend to learn about. If you think about it as an equivalence class of ways of mapping to a field, then it's in a sense saying it's like a particular measurement or expectation value, right? It's like mapping all observables consistently to a particular field of numbers in such a way that extending that field of numbers doesn't matter. And so I think it's a pleasant alternative definition of the spectrum to see it in this way. Of course, we're just sort of coming up with, either way we do it, we're just coming up with definitions for the opposite category of the category of rings. So there will be many presentations for that, but it's a great question. I hope that answers it in some way.
Thank you.
Thanks. Okay. So I could, of course, ask for more. At a minimum, I probably want some dynamics. So those dynamics should be a subspace consisting of solutions to equations of motion. In a variational theory, I choose an observable to be the action functional. And then I take E0 to be the critical locus of that action functional. I have a quotient from off-shell to on-shell observables. In the variational case, deal generated by all formal derivatives of the action functional. You can think about it that way. I might also ask, this is sort of a main thing that's been missing so far. Might also ask for some form of Noether's theorem. That means that observables on E is really a correspondence from observables on E to symmetries of E. This is something that applies to most theories we tend to think about. And it plays, I guess, a big role in quantization. So, for example, in classical mechanics, oh, sorry, and this is an on-shell thing. So this is really observables on E0 and symmetries of E0. In classical mechanics, E0 is certainly the phase space. It doesn't matter whether I use a first or second order formalism. And that's important to mention. So the spaces E may differ. E will be either the space of maps to the coordinates or the space of maps from time to coordinates and momenta. Those are both very big spaces. E0 will just be the phase space constructed in canonical fashion. The phase space is always isomorphic to the space of solutions to the equations of motion, space of Anschauung trajectories. And the correspondence is the one that people are familiar with from the Poisson bracket. So this says that observables generate Hamiltonian vector fields via the Poisson bracket. This means that if I have some function in obs 0, E0 has a symplectic form, which defines a Poisson bracket on obs 0. And I can ask that the symplectic form, so let me say, the symplectic form is called omega. And I could ask that omega of x sub f, omega is a 2 form on the phase space. If I contract with a vector field on the phase space, I get a 1 form. And I can solve the equation that says that the 1 form df is the same as the 1 form I get by contracting the Hamiltonian vector field with omega. So this is the equation that defines xf. And that actually sets up a correspondence between observables on ob 0 and transformations, symmetry transformations of the phase space into itself. A vector field is just an infinitesimal self-map of the phase space, right? And Liouville's theorem says that I guess Liouville's theorem says that these vector fields are Hamiltonian, so they conserve the symplectic form. So they're kinematic symmetries. For them to be dynamical, they have to commute with the Hamiltonian and so on. But this is a story that you all know. From my sort of general nonsense perspective here, Noether's theorem is essential, but it's really the special ingredient here. So almost everything I was doing otherwise was just something about studying a general subspace of a very general space E. E0 didn't have to have that many properties. The fact that E0 is equipped with enough structure to give me a form of Noether's theorem, right? Noether's theorem really says that I have a correspondence of this kind precisely when I'm in the variational case. So I just want to say that's sort of the most non-generic or hardest to get in examples. And everything we've said so far was classical. So now you could ask about quantizing. And quantization is really an interesting case because this is the first time that C appears in an essential way. So everything we've done so far, often I'll use R all over the place in building these models. For example, I might take sigma to be a Riemann surface defined over R, or sigma to be the real line in the case of quantum mechanics. And I might take X to be a real vector space. And then E is the space of maps from R to Rn that are continuous with respect to the topology on the real numbers, or smooth, so differentiable with respect to the definition of derivative using the algebraic operations on R. So the real numbers, or some field, ideally some field with a topology, that's been implicitly used in a lot of these objects, at least when we go to construct concrete models. Nothing there really essentially uses C in most models. So for example, I write down theories of maybe complex fermions, but often you can sort of get away, it's not quite true. So for scalar fields, let me say, a complex scalar field is really just a fancy way of writing two real scalar fields. There's nothing essential about the algebraic structure of C as opposed to the vector space R2 that's important there. You maybe need the complex numbers a little bit for fermions. For example, when we talk about there being a Weyl spinner in 4 dimensions, that's a genuinely complex representation of this spin group. You could ask for a Majorana representation, which is real, but there's a unique Majorana representation. The Weyl representations, the chiral spinners, are intrinsically complex. And so there's kind of not much of a way of getting around the complex numbers there. Although I would argue that whenever you're talking about fermions, you're already sort of talking a bit about quantization anyway, because the spin group appears as a, and so the fact that you have on your hands and say that that's the case. Of course, there is a real spin bundle, but we explicitly ask for them and never do quantum mechanics with any other field other than C. We're sort of, as physicists, because we say, well, some of these numbers are imaginary. I can't measure them. And so the whole fact, and it changes the way that quantum mechanics behaves in a really essential way, because sort of the whole structure of probability theory in quantum mechanics is not the structure of classical probability theory. It really has to do with something essentially different. And there are sort of good reasons physically motivated reasons that C appears. And not some other field. At least here. So it's 7 p.m., which probably means we should take a short break. I think what I'd like to talk about when we come back is sort of 3 ways that you might hope to introduce the adics. And then I'll sort of hope to deal with those one after the other and talk about some interesting and more concrete models in each case. Great, okay, are there questions at this point? Maybe I should break for about 10 minutes, 5 minutes.
Are there questions?
Yeah.
Okay, so see you in Dennis 12:10.
Sounds good.
Thank you.
Thanks, guys.
You guys have 10 minutes.
Ya vamos a retomar.
Okay, we are ready, Aymar.
Okay, great. I think I'm ready too. So welcome back. I guess what we've gotten to so far is that you might imagine several different types of generalizations of the sorts of objects that we've written down, which would lead to sort of various different generalizations of physical models with an arithmetic flavor or with a p-adic flavor in all cases, but where those sort of differ concretely in what is happening. So we've got sort of a four-step process where we could choose sigma. We choose X, we consider maps between them. We take E to be maps from sigma to X. and observables to be some kind of functions on E. And then maybe, for example, we choose on-shell things which look like this. And then we have quantization at the end of the story. And that typically means that we build H, the Hilbert space, as some, at least if we think about geometric quantization, some appropriate subspace of complex functions on E0. So for example, if E0 is the phase space for classical mechanics, it's a real space. It happens to have a symplectic form, and we sort of polarize it by splitting it into positions and momenta. So we choose a complete set of commuting observables, maximal Poisson commuting subspace inside of OBS 0. What do we do then? We construct the Hilbert space as the complex valued L2 functions that are functions only of the position. So it's the complex valued functions on E0, which are independent of momentum and square integrable over the position. And that's sort of the traditional way that you end up constructing quantizations of such systems. And I want to emphasize that when we quantize, the sort of Noether's theorem data entered in a subtle way. Namely, when we said what it meant to be Poisson commuting, we used the information of the symplectic form here, or the Poisson tensor on the Poisson bracket on observables. Maybe I'll write this as a Poisson bracket. So in the classical world, the story is pretty straightforward. It uses this subtle extra piece of data that comes from being a variational problem, the symplectic structure that lets me go back and forth between flows and observables. And then quantization makes reference to that Poisson structure or bracket structure in kind of a slightly subtle way. And I need to pick out some subspace of complex valued functions on E0 in order to do it. So at least in geometric quantization. And so you might ask, where can I generalize? So one answer would be replace OBS with some more general commutative algebra. And take E to be spec OBS. Then I sort of have to think about what quantization means. And probably the path integral is the most promising way to do it. you could imagine replacing sigma with a space defined in a different way. So we haven't really said anything about how sigma is defined, but for example, when sigma was the time, it was just the real numbers. And in string theory, sigma was a real manifold. So when I say generalize, I mean replace it by something other than a real manifold. And actually, there are lots of examples of this. Many, many, many. And not just in p-adic models. So replacing sigma with some less structured space is sort of one of the most common things you can do. So for example, you could take sigma to be a graph. Often you'll do this like in lattice models. The Ising model, something like that. That means that I have degrees of freedom. I may be doing a statistical mechanics kind of model, and my degrees of freedom are located at discrete points. I label them by discrete labels, but there's still some notion of distance. For example, I know when they're neighbors. The structure of graph tells me a little bit about the geometry of the way those degrees of freedom are distributed in space or distributed geometrically in some fashion. What else could sigma be? Sigma could be something like the p-adic numbers, or it could be the p-adic vector space, or it could be something like the Riemann-Surfaces tree of QP. That's also a graph. And this occurs really many of the p-adic models one looks at are of this type. So in fact, every model I think that I've ever studied in a very concrete fashion has been of this type. So for example, p-adic string theory sort of fits into this part of the diagram. There I consider maps from a p-adic world sheet. So remember in string theory, sigma was the world sheet. The target space where you imagine yourself as living is still a real space. It just has some coordinates on it. And so in p-adic string theory, you think about a theory of maps from a p-adic world sheet, which in fact, often, depending on whether you're doing open or closed, could be this tree, to a real space-time. And in that sense, the deviation from a standard theory is minimal because you're just constructing amplitudes. So in a typical string theory, you get scattering amplitudes using the correlation functions of a two-dimensional conformal theory. And that's exactly what you do in p-adic string theory. Of course, it's a p-adic conformal field theory in a sense, but you just write down scattering amplitudes in real space. I guess this has been discussed a lot. There are also other examples of p-adic field theories. Which are sort of theories of real fields on p-adic spacetimes. In the context of quantum field theory, you would say, now I've replaced, remember in a field theory, sigma is the spacetime, so you would say the spacetime is p-adic. But the fields, so the degrees of freedom, are real, and the space of maps from sigma to x is just a real vector space because X is a real object. And p-adic alias CFT sort of also fits here. There you sort of compare a p-adic field theory to a graph model, which is defined on this tree, using the fact that the boundary of the tree is identified with the projective space over the p-adic numbers. You could also do other things. You could take sigma to be, for example, a cyclic group, or Z modulo NZ. And in fact, one often does this, right? This is a lattice model with periodic boundary conditions. And so I sort of want to emphasize that many p-adic models, the ones that just replace sigma and not X, sort of fit into a very standard set of things one could do in physics, which is just to parameterize the degrees of freedom by a different kind of object. And normally when one does this, one takes, for example, the integers or some graph. You do this in order to get some good properties like being discrete at the cost of, for example, breaking symmetries. The integers don't have, or lattice over the integers doesn't have really a great set of rotational symmetries. It's just some discrete set of lattice transformations. When you work over the p-adic numbers, the resulting field theories that you get really have a lot in common with normal field theories, because almost all of the structures that one uses to build a normal field theory come from the fact that R is a local field. You often, for example, do Fourier theory. You write things down in momentum space. You take various products of additive and multiplicative characters of the field and integrate them over additive and multiplicative Haar measures. And most of the things that you do involve using that geometric structure to better understand the space of maps from your local field to wherever the fields take values. And in that sense, p-adic field theories of this sort are really a pretty minimal departure from more standard models. It's perhaps to be contrasted with the example in 1, which is quite a dramatic departure. If I say the observables of my theory are the integers, or the Gaussian integers ZH on I, then there's still a sense in which I can fit it into this package that I'm describing, but less of the standard machinery is lying around for me to make use of. Sort of another point I want to emphasize here is that for field theories, how do I want to say this? On vector spaces over local fields, many results are actually universal. So independent of the place I look at. And that's more or less for the reason that I said in words a moment ago. It's because often a field theory is a recipe for constructing certain objects like anomalous dimensions, correlation functions, or whatever, by combining ingredients that can be defined at each place in more or less the same way. Combining, for example, additive and multiplicative characters and integrals in some fashion, where if I take care to define things appropriately, I can just take the characters and integrals that are appropriate to the place, derive the result in the same way, and I'll get something which is expressed in terms of special functions that depend on the place, but in a universal fashion. This is something that was really emphasized in the work of the late Steve Gupser. So Steve died a few years ago now in a mountain climbing accident, very unfortunately, but he was a great advocate for the study of p-adic field theories, and I think he found it very profitable and did a lot of good work there, and he would have really enjoyed being at this meeting. So it's good to remember him here. We can replace x. This is another thing we can try to do. So I think most often, one takes both sigma and x to be p-adic. I don't know that there's necessarily much of a reason to not think about sigma being real. You'd be hard pressed to find what kind of maps you might want to think about. But in any case, the effect is that E becomes some kind of p-adic space. So perhaps some vector space. Over QP. And the main example here is really sort of these theories of p-adic quantum mechanics. And sort of other theories of p-adic particle motion. This is perhaps slightly more radical. Number two, at least from some perspective. But it's interesting, and there are models that you can write down that are good analogs, for example, of the harmonic oscillator, other quantum mechanical systems, free particle motion. And I think it's important and good to keep these models apart in your head, because in number two, we really have standard degrees of freedom, maybe real degrees of freedom. They just happen to be parametrized by something whose geometry or structure is controlled by the p-adics. In three, we have a theory of p-adic degrees of freedom. P-adic string theory, for example, is not, from this perspective, a theory of a p-adic degree of freedom. It's the last thing you really might try to change. We've sort of We've thought about changing the observables just in an ad hoc way. We've thought about changing sigma, and we've thought about changing x. Changing x is more or less the same as changing E, at least the sort of kind of object that E is roughly the kind of object that x is. So the last thing we might try to change is H itself, the Hilbert space. And you might ask if there's an interesting way of doing that. And there are sort of candidates, like you could imagine, for example, looking at p-adic valued functions on E0. But in fact, there are very, very strong constraints on this. So I'd like to discuss one of these constraints. My plan for the remaining time, more or less, is to work backwards. I'll start by discussing some of the constraints on option 4. So in option 4, they're sort of interesting, in a sense, non-Archimedean analogs of Hilbert spaces. But all of those analogs of Hilbert spaces, and I'll be precise in just a moment about what I mean by an analog of a Hilbert space. All of those spaces are kind of unsatisfactory for one reason or another. Unsatisfactory will have to do with the assumption that there can exist infinitely many roughly speaking, orthonormal basis vectors. So a characteristic property of Hilbert space is that I can make one that's big enough to include as many measurements as I want. And in particular, I can find a countable basis, which is some infinite collection of orthonormal vectors in the Hilbert space. And it turns out there are these very interesting results which say that under some weak assumptions that don't take any field for granted, they just sort of ask about the logical structure of propositions in quantum mechanical theories. You can derive that any category of objects satisfying appropriate conditions is equivalent to the category of Hilbert spaces either over R or over C. And it's really, I'm sort of in a sense shocked that these results exist because normally it's very hard to sort of derive a choice of field from assumptions that don't on the face of it have anything to do with that. But in fact, it works. There's in fact some recent work on this that I'll cite in a moment. So I'd like to, with the rest of the time today, maybe discuss, in a sense, why 4 is complicated or difficult to deal with, and why the Hilbert space is a pretty well-motivated way of talking about quantum mechanics. And then in the next few hours tomorrow, I'd like to sort of work backwards and talk for a bit about models of p-adic quantum mechanics, and then spend, I think, the bulk of the time discussing examples of theories that are built just by replacing the parameter space by the p-adics, and connect back a bit to the theory of renormalization and scale transformations. That's the plan for the remainder of the time. So let me talk a little bit about point 4 and some of the constraints that exist on finding interesting generalizations along the lines of point 4. So a somewhat older theorem by Soler, related to what in that literature is called an orthomodular space. The sort of key background idea is that quantum logic is different than classical logic, but it's different in a way that we can understand. So in classical logic, we took the sort of true-false propositions are sort of subsets of E. And they all sort of take the form is the observable F in some range U. Quantum mechanically, we need to think a little bit harder about how true-false propositions should work. We can ask, is the state annihilated by some observable O hat? Let me call it F hat. Another way to think about what this is saying is really, when I measure the observable F hat, is my state an eigenstate of F hat with the eigenvalue in some range? And that means that the propositions are more or less closed subsets, closed subspaces of the Hilbert space. I can ask, for example, is the state in this closed subspace? And I can formulate these in terms of projection operators. And there are various sort of operations on these closed subspaces. For example, I can take the orthogonal complement, which corresponds to sort of a logical knot. I could take the tensor product of Hilbert spaces, which corresponds to concatenating systems. Sticking two systems together. That's of a slightly different flavor. It has to do with the category of Hilbert spaces rather than a single Hilbert space. In the category, within a single Hilbert space, the really important operations are the orthogonal complement, which is sort of a knot, the intersection, which is sort of an and the span. The span is really like a quasi-or. And a lot of the issues in quantum logic I mean, if you think about entanglement or something like that, it has to do with the fact that the span is not really an OR in the same way that the union is an OR in the logic of sets. For example, if I have a proposition, if I have two propositions, two closed subspaces, then a state can be in the span of them without being in either of them independently. So OR doesn't behave the way you think it should in quantum mechanics. But there's one key proposition. Which is that I can always take the Hilbert space and write it as the V, if V is a closed subspace of Hilbert space, plus its orthogonal complement. So this is, if you like, in logic terms, what is this saying? This is saying V or not V. So it's the law of the excluded middle. So what did Soler prove? She proved that if H, so an orthomodular space is really just going to be a vector space over a division algebra. So it has a notion of not, it has a notion of and it has a notion of or. And what's that? Not orthonormal, modular. And that's an infinite orthonormal system. The way you should think about an infinite orthonormal system is a collection of infinitely many subspaces, all of which are closed subspaces, all of which are orthogonal to each other, and all of which are distinct. Orthonormal means that there's vectors in those spaces that have length 1. Then K is R, C, or H. And curly H is a Hilbert space. Over K. So from my perspective, this is a really remarkable theorem in a sense, and this was recently used. To prove the following. This is a result of Riemann and Cornell from last year. And I'm not going to state it especially carefully, but it's It goes roughly as follows. If C is any category with a dagger operation, that means that if I have a map in this category from an object H to an object K, I have a way of getting a map the opposite direction. Which squares to 1. So the dagger of a map, the dagger of the dagger of a map is the map again. In the category of Hilbert spaces, this is of course going to be the dagger operation, adjoints. But abstractly, you should imagine that if I have a subspace of a Hilbert space, I need to know not only how this subspace includes into the bigger Hilbert space, but also how I can project onto the smaller Hilbert space. That's what this dagger is telling you. If it also has a tensor product with a unit, and the unit is simple enough, so it has no interesting sub-objects. And if the unit separates this means I can check the quality of morphisms. On H tensor K using pure states. Pure is a bad tensor product states. So this is maybe slightly technical, but really what it means is the tensor product basis exists. And it's enough to check things on a tensor product basis. Nothing weird happens for entangled states. There's a coproduct. And of course, I want these things to be compatible with the dagger operation in an appropriate way. So a sum with a unit, the zero vector space, equalizers exist. This is the version of and. This is just a categorical way of saying this. It says that if I have two maps between Hilbert spaces, H and K, an equalizer is a universal object that maps in like this, such that F after E is the same as G after E. So this is effectively just taking the intersection of the kernel of F and the kernel of G, roughly. And direct limits of injective systems exist. This is where infinite dimensionality creeps in. But physically speaking, this is saying I can approximate a Hilbert space by considering successive finite dimensional subspaces. So it's a reasonable thing to ask for. And any injection this is a technical condition, an equalizer. Of some map and 0. So this is really saying quotients by subspaces exist. So C is a category that has these things. It's some list of properties, but none of them refers to a field at all. And the theorem says that then C is the category of Hilbert spaces over either R or C. But it's a really interesting angle. So effectively, the way this goes is you observe that in this category, you can reconstruct the field by taking the endomorphisms of the unit object. So in Hilbert spaces, the unit for the tensor product is C, the one-dimensional Hilbert space. The endomorphisms of that Hilbert space are complex numbers, non-zero complex numbers. And if you include the 0 endomorphism, which projects to a point, then it's just the complex numbers. And so what you do is you start by considering the endomorphisms of the unit object here. Those are just ways of mapping the trivial Hilbert space into itself. And you show that that's a field. Takes some time, but you can show that that's a field, and the objects are sort of naturally vector spaces over that field. The vector space multiplication by scalars comes from a natural map in the category. And then you apply the theorem from above. You sort of use the fact that direct limits should exist to find an object that wants to have a countably large orthonormal system. And then you apply the theorem from some time ago to show that if you have an object which is a vector space over something, and it has this countable orthonormal system, then it has to be a Hilbert space. And I think one of the dagger conditions excludes the case of the quaternions. So I wanted to mention this theorem because I found it really kind of a fascinating answer to a question I've had for a long time, or a fascinating attempt to answer that question, which is, why do the complex numbers play this role that they do in quantum mechanics? Why is it that when I think about the Hilbert space, I have to think about the complex valued functions? It's completely not obvious to me. And this is in a sense an answer. It says that if you have a sort of logic that works the way that quantum logic normally works, in the sense that it works analogously to the way the closed subspaces of Hilbert space work, and if you ask for some sort of weak additional conditions, then you find that that object automatically has to belong to a category which is the category of Hilbert spaces. And so this sort of fits in a sense, to this collection of reconstruction results that we've been talking about. So the first reconstruction result that we mentioned today was this sort of stone reconstruction theorem, which says that if I have an abstract classical logic, like an abstract Boolean algebra, there exists a space such that that's the concrete logic consisting of the subsets of that space. We talked about the version for sigma algebras, then we talked about spec. What spec more or less is a reconstruction theorem that says if I know the algebra of functions on a space, then I can reconstruct that space by taking the spectrum of that algebra. And this is, in a sense, is also it's also a reconstruction theorem. It says that if I have a logic, if I have a set of propositions that behaves the way that true-false propositions behave in quantum mechanics, then I can kind of reconstruct, as I've stated it doesn't allow me to reconstruct the Hilbert space, but it allows me to reconstruct that my logic is the same as the logic of closed subspaces in some Hilbert space. The dimension you have to check, but so in a sense, this belongs in my mind to the family of reconstruction results that we've been discussing. And it's impressive because the field comes out of nowhere. So for example, in the way we formulated spec, it was really about making, setting things up in a way that we were agnostic about what field we were even talking about. And it was totally fine to define the spectrum in a way that only referred to a field indirectly. Even if we wanted to think about measurements as being maps to fields. This reconstruction theorem is very much not of that type. It says that somehow the complex numbers or the real numbers come out of nowhere. So I think it's very much worth mentioning in this context because it sort of sets an interesting outer boundary to what you might hope to be able to do. I'd like to mention there are interesting examples. Where the law of the excluded middle holds. But no infinite orthonormal system exists. So I guess Keller in 1980. Built such a space as more or less as an L2 space functions with values in a non-Archimedean field. And in fact, it's a non-Archimedean ordered field. The thing that you end up using for some strange reason is you take the direct limit of the field of rational functions in n variables over the rational numbers. And then you complete it in some way. And then you define an L2 inner product on sequences that take values in this very strange field. And it actually gives you an example of a Hilbert space whose subspaces, I mean, it's viewed as an orthomodular space. Its subspaces satisfy the law of the excluded middle, but no two vectors no two perpendicular vectors have the same length. So I think since then, people have constructed ones that have finite orthonormal systems, but this doesn't even have an orthonormal system of length 2. Any two perpendicular vectors have different lengths. So this is just an interesting thing that you might come across in the context. And I sort of want to mention it, not only because it's an interesting example, because it comes up in the context of L2 spaces with non-Archimedean values. Yeah, I think this theorem was the last thing I wanted to discuss for today, and we're more or less out of time. So next time, I think I'd like to pick it up in the first hour by discussing theoretic quantum mechanics. And then in the last 2 hours, I'll discuss models. How did I number these? Exactly. So having said a little bit about option 4, I'll work backwards and start by discussing option 3. And then spend probably the most time, the bulk of the time tomorrow, on option 2. And then if I have time at the end, maybe I'll say a bit more about option 1. Option 1 is, I think, interesting and worth exploring. I'll leave it at that for today. Thanks, everybody, for your attention.
Thank you very much. Are there questions or comments? I have a question, Igmar. The result that you presented is very interesting and technical. The result in this, I'm not sure. This result implies that the wave function should be complex valid.
I think that's a way you can interpret this result.
Exactly.
So,
or like, that the let's say the observables as operator must add on complex valid functions.
Right. It's saying that if you want the standard sort of probabilistic interpretation of the quantum states, then the observables should act in some complex Hilbert space. I think that's a consequence. I mean, of course, you have to be careful about exactly what you're asking for in the conditions of this theorem, right? But it has the effect of implying that that should be true in general when quantum mechanics works the way it normally does at the level of like true and false propositions. I think maybe you don't even need the Born rule to do this. It's in a sense even weaker than the Born rule, maybe.
This theory doesn't say anything about the structure of the space-time at very short distances.
No, I don't think so. In a sense, you can interpret it as saying the Hilbert space should be a Hilbert space of a familiar kind. But I don't think it says anything about the space-time. So in a sense, it happens entirely in the last step. And what the space-time is somehow going to be, the way I think about it schematically is that the space-time is somehow coming from the notion of locality. So I imagine that my Hilbert space is maybe decomposable as a tensor product into some factors where those factors are associated to like local pieces of the space-time. And I don't think this theorem has anything to say about the way that the geometry of the space-time emerges from that tensor product decomposition or the way that encoding works. I think it just says that you don't lose anything by assuming that all of those Hilbert spaces are normal Hilbert spaces. At least if you want to make use of the assumptions.
Thank you. So let's hand the speaker again. Then see you tomorrow at 9:30 local time in Mexico. Bye-bye.
Right. Yeah, thanks so much. We'll see you tomorrow.
Okay. So guys, now we have the lunch. Thank you. You're not needed.
Thank you so much.
No, it was a very interesting.
Yeah, I hope
It
that was the
a
right.
very, very interesting talk.
Thank you.
I'm going to ask you additional questions.
Please, yeah. I hope it was the right speed for people. I wasn't sure exactly about the background, but I know people know the p-adics and they've seen, p-adic string theory and this kind of thing. So I figured maybe some bird's eye view is not so bad.
No, it was good. Thank you.
Okay. Yeah, thank you.
See you tomorrow.
Yeah, we'll see you tomorrow.
No. They are asking about the notes, your notes. It would be terrific if you can send me your notes as a PDF file.
Yeah, I'll send you.
And then I'm going to upload the notes in the website of the conference.
Perfect. Yeah, I'll send. I mean, it's totally easy to send what I was writing today.
Yes. That's good.
Plug it in one file and send it.
Please.
Is it helpful to give? I can give references to some of these papers. Maybe
yes, that would be terrific.
Yeah, I'm happy to put some of those together.
Thank you. See you tomorrow.
Yeah, thank you. Good to see you, Wilson.
Hola Hugo, ¿cómo estás? ¿Me escuchas?
Sí, ¿qué tal, Wilson?
Bien, bien. Oye, te iba a decir lo siguiente. Cierra la puerta mientras. A ver si a ver si hablo. Cuando que nos des, después de 50 minutos, nos des un receso por ahí de 10 para descansar. Si puedes
Sí.
hablar 50 minutos, descansamos 10.
Ok, perfecto.
Sí, que es un recreo.
Sí, está bien, no sé,
Porque es
la vez
2 horas
pasada se me
seguidos.
fue la onda.
Sí, sí, yo te dije.
Sí.
Es muy duro porque sí es. Pero entonces, no, ay, ¿qué pasó?
Me está preguntando al micrófono acá algo. No sé si. ¿Cuál es la grabación? No. Yo quiero eso. Sí, no, sí, mejor que una control. No, aquí te hablo. Ahora llega un poquito más de gente. ¿Y el artículo? Vamos a comenzar entonces.
Good afternoon, everyone. Today is the last part of the course by Professor Pompean on non-Archimedean string amplitudes. Please proceed.
Okay, let me to share the presentation. Can you see the presentation?
Yeah. Yes.
Okay. Okay. Thank you very much. We continue with the lecture. Well, the second lecture is the application of what we saw the last time regarding the generalities of amplitudes. So one of the interests of these applications of periodic or non-Archimedean in general tools in the process of scattering is the interest is encoded in this transparency, where there is a lot of people working in this subject in the context of ADS-CFT. There are a lot of there was the last years there was a lot of interest and papers on this subject. In fact, one of the speakers of this conference, of this school, is Igmar Saveri, who is giving a course today and tomorrow. He will finish tomorrow. So there is a lot of subjects regarding scattering amplitudes in the context of ADS-CFT. Is a subject of string theory. So this is only to show a little bit about the interest of this in this subject. In the second lecture is based in the papers, in these papers. Actually, this paper, this is a review, it's an overview that was published in the journal Symmetry the last year. So I will ask to Wilson that he put this paper in the memories of this school, in the part of this course. So this is a very good reference, and most of the things I will say in this talk is contained in this paper. Okay, so our group is quite active in this subject, so I hope to convey some of these inquietudes, some of these kind of things we are doing in the last years. So let's start by recalling something about the Polyakov action in string theory. The Polyakov action is an action, is a energy, functional energy for an embedding map, which is possible to write down in this way, where sigma is a Riemann surface with genus G, B number of boundaries, and N is a number of the number of market points on the surface. So in the case when we have some boundaries, we have an additional boundary term located precisely in the boundary. In the first term, we have a differential operator, is the Laplace-Beltrami operator in 2 dimensions and on the surface. And X are the embedding variables, is embedding mapping, which are the relevant variables in this context. Nu is an inserted operator in some points of the boundary. Okay, so the scattering amplitude can be computed in this context in a string theory via the Feynman integration of the modular space. with a surface, Riemann surface with this characteristics. So the amplitudes are assumed over all the genus, over the genus of the surface, weighted with a string coupling constant, which gives a notion of how large is the interaction of these strings to the Euler characteristic of the surface. And multiplied by this function. Thus, where this function is actually the Riemann surface, the Feynman integral integrated over the modular space of Riemann surfaces with these parameters. Okay. So we will restrict to the case of, well, in general, this Riemann surface can be an oriented surface or an unoriented surface. This can be a Klein bottle or a Moebius strip or any other, some kind of theories called Taiwan theories, Taiwan string theories, has unoriented strings, unoriented surface. But in our case, today we will speak only on the oriented case. Okay. So these amplitudes for some genus, some specific genus, will restrict to the case of genus 0, and genus 0, sorry, and one surface with one boundary, B1 equals to 1, and the amplitude is with 4 vertex operators. So we will restrict to the disk, to work on the disk, with 4 market points, with 4 tachyons, vertex operators. So this will be the 3-level amplitudes with 4 points. This is the Venezian amplitude. So the art of compute the scattering amplitudes is the art of solving this integral, which I mentioned before, that this is a very complicated only for some specific cases of some choice of the genus, the genus, the number of boundaries and the number of market points is this integral is possible to carry out. But in the most part of situation, this integral is impossible to perform. So the art to compute the scattering amplitude is a very difficult problem. Okay. Well, so for this case, in the case of the disk, this integral and this scattering amplitude, this integral is reduced to the Veneziano amplitude. How I argued in the last lecture. S and T are the Mandelstam variables, which are the square of the momenta we have 4 momenta because we have a 4 particle scattering. So this is the integral, which is basically the beta function, which is the product of Euler gamma functions divided by the gamma function of the sum of the arguments. This is the case which will be interesting for us. For x are the points on the boundary of the disk. So this integral is one-dimensional. This is for the open case. For the closed case, this integral is two-dimensional because in the closed case, the number of boundaries is zero. So there is not insertion in the boundaries. The insertions are on the two-sphere. And the two-sphere is parameterized by two complex numbers. So the amplitude is for the closed case is called Virasoro-Shapiro amplitude, and this is a matter of another talk. We will restrict. I said to this to equation 1. Okay. This integral converge is very well known. That the integral converge for some values, some choice of the parameters of the cinematical parameters of the momenta, and so this integral exists and is convergent for some choice of the parameters, and this is for the 4 dimension is more or less, sorry, for the 4 points is more or less very well known. But in general, for the endpoint, I mean working on the disk, but considering no 4, but endpoint amplitude, the general case. This the choice of parameters in order to check where the integral is convergent is nothing easy. So there is a comment given by Witten, Edward Witten, in this paper, the Feynman I epsilon in string theory. In string theory, so they E epsilon is a way of precisely to find the space of the region of the momenta, in which is possible to find some convergence of this integral. So this is not an easy problem. The general comment is, for general n is unclear that there are any choices of external momenta for which the integral converges. So the problem of to find the region of convergence for this integral for the endpoint amplitude for the general case is a problem. Okay. In the real case, not in periodic, but still in the real case. Also in the paper by Witten, he mentioned the following: the region in which the integral converges is often empty and never suffice to describe physical string theory scattering processes. A general string theory amplitude does not have a safe region, so one needs a better approach. And in this paper, he mentioned various approaches to find regions where this integral exists. And one of them is the splitting the integral, Poch-Heimer contours, continuation from the Euclidean signature, precisely the Feynman E epsilon technique. So for the 4 points amplitudes, all of them are implemented, and it's possible to show some equivalence between some of them. But in the endpoint, for the endpoint amplitudes, actually there are only the Feynman E epsilon is the only one that has some success with respect to the others. The others are implemented only for the 4 points amplitudes, and they are very complicated. They are very difficult to extend to higher number of points in the amplitudes. In this regard, this paper by William Bay and Wilson, they precisely use the techniques of the periodic, which we implement in the periodic case, but for the case of the real and complex amplitudes, in order to find the regions of where this integral exists. So this result 2 years ago goes precisely in this direction. So it will be important, it will be interesting to find the way of the technique of find the region of integration, or where this integral actually exists, with some of the other techniques. This will be a very nice thing to do for the future. So I only mentioned this as a possibility here. Okay, I'm not going to say nothing about the closed case. So I know you are expert in the periodic numbers and integration. You have several courses and talks in this school. So I only going to mention some remarks in order to introduce notation and conventions. So periodic numbers are precisely can be constructed from the rational numbers by adding Cauchy sequences using the periodic norm. This is one possibility. And the other possibility given by the Ostrowski theorem is to take the norm with p goes to infinity, which gives the real numbers. So the idea is to consider scattering amplitudes in string theory, where instead of having the real norm, we have the periodic one. this will be the idea. So a p-adic number is an element, is written in a formal series in powers of p, where p is a prime number, is any prime number. So the coefficient of this expansion is bounded or limited between 0 and p minus 1, depending on p. The norm of the, if X has this structure, this is this expansion in series, the norm of the p-adic norm is precisely p to the lowest power with this negative sign. Okay, of course, what AK is the coefficient of this power is different from 0. In general, the norm, the p-adic norm is an ultrametric norm. So the definition satisfies this ultrametric condition. And the saturation with the equality is precisely what we have this case. Regarding the topology of the p-adic numbers, which will be important for us, is in general, p-adic numbers are the unitary ball cross Cartesian product, the complement of the p-adics, which will be defined in a moment. The units, sorry, the p-adic integers are precisely the elements of QP, whose norm, a p-adic norm, is lower or equal to 1. So these are balls with a radius 1, the unit. There are various versions of the p-adic integers. So one of them is this, where we have the product of from g equal to 0 goes to infinity. Or another version is precisely related with the topology of the p-adics, where C cross is the units, p-adic units. This is an Abruchatitz tree. This is a discrete diagram which contains precisely this structure. Here, UP in the notation is precisely C cross, CP cross. So we have the p-adic constructed from the p-adic integers plus something else, the complement. And the p-adic integers are precisely the in this version is this, and we consider the product of them. Are the balls with radius lower than 1. And this will be the radius, the balls with radius greater than 1. Okay, this will be enough for the integration. Okay, before that, we mentioned a theorem of André Weil, which tells us that QP is a topological group with a sum. With a sum is a topological group there is a unique Borel invariant measure, which is the Haar measure, which is invariant under translations. So this integration over Q of this Haar measure is equal to the integration of some translation of p-adic numbers by the same numbers, where the measure is invariant and under translations, and under the product, under the scalings, this is given precisely by this. This is just the p-adic norm of a constant multiplying by the variable x. So we have this for any a in being a p-adic number. Okay, before we compute the p-adic amplitudes, define the p-adic amplitudes, we will give some results, some necessary result in order to. We consider the p-adic integration over the integers of this invariant measure, invariant on the translations, Haar measure. So we normalize. We give a normalization condition, which integration about the p-adic integers is equal to 1. So remember that taking one of the version of the p-adic integers, we substitute this over here, and under this condition, normalization condition, the right-hand side of this equation is given by the sum over from 0 to p minus 1, then the number of x0, and this condition. Using the previous theorem, the Weil theorem, this integration is invariant on the translation, and this sum gives the p numbers, p times the same integral, which is p, it's a factor p, and we have the integration over p cp cross. So we can, so we don't know, well, this integration, we take this integration, we find that this integral is just p to minus 1. Okay, this is a result that we will use later. Now consider an integration of this form, integration over Cp, now with a variable with the p-adic norm to the power s. So this integral will depend on s. Once again, using the version of p-adic integers in terms of p-adic units. So we substitute this over here, and this product translates into a sum over j from 0 to infinity. So we have this a lot of infinite numbers of integrals in this space. So we can perform change of variables in order to remove the factor p. So we take x equal to p to the j times y. So this integral using precisely the facts of the Bayes theorem and use precisely the periodic, the fact of the periodic norm. Sorry. So it's possible to show that this in terms of the y variable, leaving alone CP cross. So we have this factor over here in the integration. And this is integration of over the periodic units. So this norm of these variables are y variables are 1. So the integration over units of the y is we call the volume of the periodic units. So this factor in this way, this integration turns into this result. Okay, so we will be back in a few minutes to this result. So we have seen that using this version of the periodic integers, then the integration taking now the y variables, and this is precisely this the integration over the first factor plus integration over the second factor. And the first one is precisely the volume, and the second one is precisely the previous result. This is the previous result, p to minus 1. So we can find the value of the volume of the periodic integers, periodic units. So we find that this is precisely this is given by this. So in our original aim that was to compute this integration. So the result is this multiplied by the volume, but now the volume is given by this. So finally, this integration is given by this result, where this integral is convergent for the real part of s greater than minus 1. Okay. Well, this were some preliminary results in order to try more complicated integrations. One of them is the 4-point integration, and these results we gave here are will be necessary in order to. We will take only the results in a few minutes. Okay, so in this paper, so we move to periodic string amplitudes. So in this paper is based on some proposals by Bolovich and Dragovich and company, where one of the possibilities that in order to describe the physics to the Planck scale is to to change the absolute values, the real norm, by some periodic norm, which is not non-Archimedean. It's a non-Archimedean norm. So the physics to the Planck scale should be different. It is not a continuous physics in order to use the real or complex number. So the motivation is to propose a periodic discrete norm in order to try to describe the physics to Planck scale to tend to the minus 33 meters. So it's very, very, very small distances compared, in fact, to the distances of reach in the LHC in CERN, in the biggest laboratories in particle physics in the world. So okay, so the scattering amplitudes I mentioned before for n points are the 3 level. In order to describe periodic amplitudes is to change the real norm by a periodic norm. So this and the integration over real reals to periodic to this power. So in this case, of course, dx will be a normalized hard measure. X ball phase, sorry, K ball phase is as this n-plet with K1, K2 are the momenta of the n particles associated with the endpoints. And each one of these is in fact a vector in the Minkowski space. In the Minkowski space with 26 dimensions in the bosonic open string theory. So in Minkowski space, we have a Minkowski norm, Minkowski inner products, so it's not a definite product, so we have a minus sign in one of the temporal in the time direction. So this is the inner product is not a positive definite. Okay, from what I mentioned in the part of string theory, we have the conservation laws, conservation momenta, momentum energy of this n momenta, and the masses of the vertex operator, which we are taking the operators associated with the tachyons, the vertex operator associated with the tachyons. Okay, well, the only change here is the norm. Now we have a periodic norm. So in the case of for the 4 point, we have to specialize this integral to n equal to 4. So we have integration over periodics here, just one variable, and we have in this case the Veneziano amplitude, but in this case with the periodic norm. and x is the only surviving variable, is a p-adic variable. So this is a p-adic integration over QP. Okay, after the computation, which I will be in a few minutes. So the result is given by, this is the structure of the, we have here an independent term and three more terms which are associated with the channels, the old friend channels, the ST, and U channels of the scattering amplitudes. And each term is associated with a channel, and this is shown in this in the number of the momenta associated with each channel. This integral is convergent. It can be defined that is convergent if we are restricted to sorry, this S1 is I forget to mention. We have here the momentum, the momenta in here. We change the variables in order, we define variables S, which are just the product, the inner product, the Minkowski space of two of momentum. Okay, so this momentum are real variables, and S can be complex variables. So we will find that when we promote this momentum, complex momentum, and we have that this integration is convergent, and there is a region where which satisfies precisely this the restrictions for all of these terms, all of these three terms. We have three conditions, and this condition gives a region where, which is given here, where the integral is convergent. So the problem to find the region where the integral is convergent for the p-adic version of the Veneziano amplitude is possible to find, is not too complicated, but so okay. Well, I'm going to compute this integral in an explicit way, the 4-point amplitudes for the p-adic case. So this integration here as we change this, we promote this integration to local zeta function, and forgive me to introduce this notion of zeta function before to introduce in a formal way the zeta functions. So we promote this to the complex integral, where the momenta will be complex parameters. K1 dot K2 will be S1 2, which is a complex. Both of them are complex. So this integral is will be a complexification of the real amplitudes, the physical amplitudes. So in order to restrict, to gain again the real amplitudes, we have to set the imaginary parts of this momenta equal to 0. So for the moment, we will work in with this integration, and Q will be the periodic integers and the complement of this. So we have two integrals, two integration of these amplitudes. We have the first integral over Cp, and we have a second integration. Okay, the second integration is it's far from x equal to 0, which is contained in this part, in this integration. So we have we can take x greater than 1 than 1. So it's possible to find that this integral can be simplified in this way. So we will compute the first integration, the first integral, and we take a version of Cp in this way. Cp cross, which are the periodic units, cross P Cp, Cp cross. Sorry, I omit here the cross. So performing a change of variables on the right-hand side, on the first integration, it's possible to find that this integral is the variables for P, sorry. Let me finish this computation and we will take the break. So the first integration is precisely performing the change of variables. It's possible to see that this integral reduce in variable y to this with this factor, and this integration is a case, is a result we found previously. So the first integration is given, the first integral is given by this. This is the result, which is valid for the real part of SU1 greater than -1. Okay, the second integration over the units is the units precisely is when x is the norm, periodic norm of x is equal to 1. So we can substitute this here. So we have only this part, and this integration is possible to show that is the sum of the first integral plus this is a sum over the numbers of over the p values of the integral. So we left the first quantity, the first integral for the value of 1. We separate this integral in this way. So the first part is under a change variable. It's possible to see that the result is this. And all this sum is given only by the second factor. Okay, so we have the first integral, we have three parts, and encoded in this formula. And so this is three components, three parts for these three terms for the first integral, and the last integral over the complement, and under a change of variables. And it's possible to see that this integral is given by this. We can take y to the -1 and integration over CP. And we found this is given by this factor multiplied by one of the results obtained previously. So we have an additional term to the integration, which is convergent or valid in this region. Sorry. So we have then the periodic version of the amplitude are precisely these terms, three terms, and four terms. Sorry, these four terms, and we can substitute here in the real case to take the imaginary part of this equal to 0. So we have S is equal, S12 is equal to K1, K2, and similarly for S32. And again for the last part. So in this last term, we use the momentum conservation, and we can show that this term is precisely -1 minus K2 K4. So this last term is possible to be rewritten in this way. So this is the 4-point amplitude, and as mentioned before, this has three parts, associated with the three channels of the K which are also present in the usual Veneziano amplitude. Okay, we can stop here in order to the break. So we come back. I don't know, in 5 or
in 10 minutes, Hugo.
10 minutes.
What time is it? 4:05.
Okay.
Okay, see you in 10 minutes.
Okay, see you. Change variables. So sorry.
Vamos a pedir un resumen al final del día de todas las conferencias. Esta vez viene gente, ¿no? El número de participantes debe cambiar de exponencial. Sí. Ya no aguantan más. Bien. Sí, está claro. No sé. Sí, están en el hotel. Lo que uno es que no sirve. Ya, todo con esto. Yo lo que hacía de tres partes de la derivada de un cuadro así. Pues claro que es lo que hace. Hay una vida que Sí, el problema es eso. Ahí el problema es que con la función de los reales y de los complejos, sí hay otras posibilidades, pero es más complicado. Pero bueno, ya el artículo ya hacen las posiciones unas simulaciones. No creo que sean cuando lo emiten, ahí es donde podemos trabajar. ¿Para qué nos ponemos a, digamos, a poner ejercicio? Los vecinos de ellos se encargan de la caseta de
Okay, let's resume the course. Please, Hugo, go ahead.
Okay, thank you, Wilson. Okay, let me summarize this part. We have computed the 4-point version of a Veneziano amplitude. So one of the steps in the process is to promote the integration to a complex actually the integration is over QP, but we will have complex powers of the periodic norm. So this is doesn't matter with respect to the integration, and the result is given by this expression after going back to the momenta. So the amplitudes are the physical amplitudes are given by this expression, and is possible to associate well, this integral exists, and there is a region of integration where these conditions are satisfied. given by this region. And the computation of amplitudes is possible. From these amplitudes, it's possible to extract some Feynman rules, Feynman diagrams. So there is a Feynman diagram associated with the independent term, and another 3 diagrams associated with this. The first one is this, which we have 4 points, and we have a vertex where the interaction is taking place. We have here two vertices and 4 lines, external lines. So this represents precisely this, and the sum over I and j take values from 1 to 3, and we have with this condition we have only three terms. So this x, y, a are precisely given by this Feynman diagram. This is for the amplitudes, the 4-point amplitudes, and for 5-point amplitudes that we don't compute here. We have a lot of terms, and the Feynman diagrams are these precisely. So Feynman diagrams are associated precisely in how these particles, the possibilities that these particles may interact. So this is all the possibilities that these particles would interact. So with respect to the keeping the 4 external lines. So it is well, it is obvious that if you take 6-point amplitudes or greater than 5, you will obtain a lot of diagrams, and the computation of this scattering amplitudes will be more difficult. Well, actually, is possible to see that these diagrams can be obtained for 4-point amplitudes, can be obtained from 2 rules called the Feynman rules, and the first one is this is for the general case for n-point amplitudes, is given in the vertex. In the vertex, we can the term associated with the vertex is the independent term. The independent term that in our 4-point case is given by this. And the other Feynman amplitude, Feynman rules, is given by the propagator. The propagator is are associated with internal lines. For instance, here we have a propagator. Here we have another propagator. Here we have 2 propagators. So these diagrams can be constructed from certain rules called Feynman rules. And this is a characterization of the amplitudes, very well known characterization of amplitudes in terms of that they can be obtained from Feynman rules. Another problem is to compute, to propose a theory, to propose a Lagrangian a theory, which after a field theory, a quantum field theory, in which after computing the scattering amplitudes, is possible to obtain these Feynman rules. And this is a theory it's a theory in the target space that is a very complicated theory that I will mention later if I have some time. Okay, well, this is the computation of 4-point amplitudes. This was the computation of 4-point amplitudes. In the process, I mentioned that we write this amplitude as a local zeta function. So I will define what the zeta function is. It was a local zeta function. Let K be a non-Archimedean local field, and phi a locally, given by this mapping, a locally constant function with compact support. And we have a collection of R functions, which are polynomials in these variables. S is a vector, is a R-dimensional vector, where each of these entries is complex. So we defined a multivariate zeta function associated with f and phi, defined in this way. Is just the integration with the phi, this function, and the product of these polynomial functions with the norm in K. With K is any non-Archimedean fields. It may be the periodic norm to the power S and the integration measure. So the integration is over K over this complement without the zeros of these polynomials. Okay, it is the theory, it is only the definition from the theory of the Gusa local zeta function. Is known that these functions converge. They are convergent integration, and also defined as an holomorphic function in the real parts of the powers of S. So even more, these integrals admit a monomorphic continuation as rational functions of these variables. Just the variables which arise precisely in the computation of the amplitudes. Okay. Well, so I already mentioned that one of the problems, perhaps the central problems, is to know whether the string amplitudes for general n, for general number of scattering particles, are convergent, or not. So the strategy here is to promote the string amplitudes to local zeta functions. and try to give well, some restrictions or to find constraints in order that actually the amplitudes, the extension of amplitudes, the complexification of the analytic extensions are precisely local zeta functions. And in the limit when the imaginary parts of this complex momenta goes to 0, we recover the physical amplitudes. So in some sense, this promote this to local zeta functions are a kind of a regularization of the string amplitudes, a p-adic string in the p-adic case. Okay, so defining some appropriated tools. S is a symmetric matrix with complex entries. So we have D of then. D is the dimension is given by this. Remember that we are integrating in n-3 variables. So we're integrating yes, n-3 variables. So the symmetric matrix is the number of independent components is given by this, plus 2 n-3 components. Okay, X is are these n-3 variables, removing x equal x1, and they are taking values in a p-adic field, in a non-Archimedean field. In order to be precise, we'll take the p-adic field, the p-adic numbers. Okay, so the idea is that the string amplitudes, the physical string amplitudes, to take the form of a local zeta function, and this is possible if f is given by this. We have a problem here because we don't have an evident phi function, which is locally constant and with compact support. So in order to implement this function, will be necessary to implement some additional restrictions in order to check that this will be precisely a local zeta function. Okay, this is the general case for n points. So this is an impossible problem in the case of the real case, as I said in the that was mentioned by Witten in his papers. So once again, taking the strategy of taking the integration over CP and the complement in the, here should be QP. It's the complement of QP, sorry. Okay, with this way, we will take a partition of the set, this set, in some subsets. I mean, this is a set of n minus 3 numbers. So we will take subsets of this set, this general set, of all subsets of, so we define the function which where Si is precisely one sector associated with the I sector of the, and we will take the sum over all of these subsets of this function. This function, of course, depends on I, and in this way, in the integration, in the limits of in the integration, is given here, where I is given precisely in this subset. So this integral is our original amplitude integration over QP. We take subsets of this set, and we can write down this expression as this sum over of possible subsets of this of T. So this integral, original integral, is a sum over some different regions of the periodic numbers. One of the results of this paper is that paper by Miriam, Wilson, and me, is that this integral can be written as the sum with two factors of which will be also local zeta functions. The product, I mean, this local zeta function factorized into two pieces, two local zeta functions, C0 and C1. These are associated with the CP, the periodic integers, and the complement. So we have where the power of this sum is given by this these values. The tilde is the complement of the set T in the subset A, which is running over all possible subsets of T. Well, this result is important because we have two pieces which are more simplest than the original integration. So the technique is then to find integrals which are each more and more simple, and to find some recurrence process in order to with some satisfying some constraints, in order to find a recursive method to check where these functions may converge. C0 and C1. C0 is given by this integration over Cp to this power, where F0 is given by, is still a complicated integration. And C1 is given integration over Cp with the complement of the subsets of in the complement space of this integration, which are of the type we found previously in the computation, split computation for the 4-point amplitude. Okay, C0 and C1 with this restriction in the case when we take the empty subset, they will be equal to 1, a kind of normalization condition. So, as we mentioned previously, the zeta function admits meromorphic continuations, rational functions in this variable. So, the local zeta function will be a regularization of the string amplitudes, such that we find the physical amplitudes when we restrict the S, which is a complex value matrix, to the real case. With the imaginary part is 0. So if this is the case, the physical amplitudes are well-defined rational functions of these variables, which agree with the definition of the amplitudes when it is the integration converge. So if it's possible to show that these local zeta functions are convergent, it follows that the physical amplitudes will converge also. So the part of the theorem was realized that this is actually possible for the zeta functions. We have here different zeta function for different subsets. For subset U1, U2, and imposing some conditions, complementary condition, is possible to check that the region, there is a non-empty region of intersection between the local zeta function associated with this subset. And for 2, there is a this is a non-trivial result. And for 3, there exists also this region. And this region is in a recursive way, it's possible to show that this will happen. This will occur for all of the subsets for all the partitions of the local zeta functions. So we get finally to a theorem in which the theorem in precisely in this paper, in Letters of Mathematical Physics, which says 2 things. One, the first one is has following follows. The periodic open string endpoint zeta function gives rise to a holomorphic functions on HC. This is a region. This is precisely this given is an intersection given by some forced supplementary conditions, which ensure that these amplitudes will be intersecting, has a non-empty intersection region. So this will contains an open and connected subset of CD. Furthermore, this local zeta function admit an analytic continuation precisely on this CD, denoted also in this way to avoid some change of notation. Then admits an analytic continuation as rational functions of the variables, of the relevant variables in our problem. So the real parts of the poles belong to the finite union of hyperplanes. Our equation of these hyperplanes have the form of 4 supplementary conditions, which I don't write down in this lecture. You can find the details in this paper, or in the Miriam PhD thesis, Miriam Bocardo Gaspar PhD thesis. On there you will have all the details. And the second part of the theorem is precisely when we have that for the real parts of the S of these matrix elements, positive or 0 for E and J taking values in these sets, then the integrals will be a divergent integration. Okay, these are two important parts of this. So the conclusion is that there will be a region of integration which is non-empty, and where the periodic version of the endpoint amplitudes of a string theory are convergent. I mean, these amplitudes, the original amplitudes, physical amplitudes, which seems to be is a very complicated way. This is here applies the Witten's comment about the difficulty to find for the real case and region of integration of this for the space of cinematical variables. For the real case, for the periodic case, it's possible to find a theorem where which ensures that this integral actually exists. Is not only a fantasy. There is this has some mathematical meaning and therefore a physical meaning. So for the real and complex case, in the paper I mentioned at the beginning of the talks by Miriam, Bay, and Wilson, they were using similar techniques that I explained here. They've found that the integration they applied in order to to try to, in order to find to show that these amplitudes are actually this amplitude exists for the real and complex case. That I don't discuss this part, but you can find this information in the paper by Miriam Bay and Wilson. So we have some time, maybe 15 minutes, in order to mention something. I will say this a little bit faster. Well, this was mentioned also by in the talk by Edgar on last Friday. So the construction of the proposal of the p-adic amplitudes is to change the real and complex norms by p-adic norms.
Sorry, Hugo.
Yes.
Can I ask you something before you move on? So
Yes.
my question is does there exist a physical explanation or understanding of the region of convergence of those integrals? I mean the integrals attached to the amplitudes.
Well, yes. In the case of in the real case, this is precisely the region of integration that I don't know if you attended the lecture on Friday, but I gave a region of integration of the which is associated with the three channels of the I mean, for the 4-point integration, 4-point amplitude, there are three channels where U, S, U, and T, with the crossing symmetry, in order to check that all of these three regions are the physical region of the amplitude. So this the physical meaning is this is precisely when the momenta, the region where the momenta, the momentum of these particles are consistent with the conservation of energy and momentum, and and is you take a region outside this situation, the conservation laws will be violated. So these are not a physical situation. So in the case of the endpoint amplitude, in fact, you have the same situation. Something but in the case of 4 points, is more easy to see the physical meaning. But it's possible to argue that for the endpoint amplitudes is also the physical interpretation of this region is consistent with the physical physical conservation laws of energy and momentum.
Okay, thank you so much.
Well, I was comment about the change only in the amplitudes by the periodic, nor by from the periodic from the real norm to the periodic one. So So it was just a change at the level of the scattering amplitudes, but they was not a derivation from a string theory coming from first principles. I mean, as we did for the case of string theory and the real case, which we gave a theory for an embedding of a Riemann surface into a target space, and compute the Feynman integrals for in the real case or complex case. This work for the periodic case was not done, was not provided. At this level, this was this come precisely by the work of Zabrodin and Spokojny and some other people, another group by Maeda and another guy, I don't remember. Okay, but they propose in a very nice papers. I recommend the paper by Zabrodin in Communications in Mathematical Physics, where they consider the worksheet, I mean the analog of the Riemann surface, the analog of the disk, the Bruch-Titz tree, and he considered a theory for embeddings of this Bruch-Titz into Minkowski target space. So the non-Archimedean nature of the amplitudes will come from the change of the nature of the worksheet instead of the nature of the target space. The target space will be the ordinary space-time, but the worksheet is the surface generated by the propagation of the string. This will be a non-Archimedean space, and so and the boundary of this Bruch-Titz will be the periodic numbers. Well, the projective periodic numbers. So it's a compact space. This will be the analog of the disk, and the boundary of the disk where we are inserting the vertex operators, the tachyonic vertex operators, are points in the periodic line. So the analog of the Virasoro amplitude here is will be a discrete action, which Zabrodin and Spokojny shows that this action can be obtained in the boundary, and this action is written in terms of a derivative of a Vladimirov derivative. So this action, the Zabrodin action on the Bruch-Titz, and the other way of writing the action in the boundary is in non-equivalent way is the other one, that is the integration over the periodic line. Okay, this one of the things I wanted to mention. Another thing is is that this amplitude for the point amplitude computation for the four amplitudes. I mentioned that this is the result, and it's possible to associate in this work of Beck, Freund, Olson, and Witten. They give Feynman's diagrams and Feynman rules, and the theory that there is a theory in the target space, in which is a field theory, is a nonlinear and non-local field theory. It's a very complicated field theory for a scalar field associated with the tachyonic field. Phi, in which if you compute this you quantize this theory a la Feynman and find the scattering amplitudes, this action was constructed in such a way that the scattering amplitudes computed by this field theory coincides precisely with the scattering amplitudes of the periodic amplitudes. So this is general for any. This is for endpoints and endpoint amplitudes. So this is a very complicated amplitude. Here we have a p to the minus 1/2 of the Laplace-Beltrami operator. So this is a Laplacian. So this is a very non-local. We have to expand this in powers of this operator. We have actually an operator and with an infinite numbers of derivatives. So this turns this action very non-local and very non-linear. But for some cases, for some linearization, it's possible to find some solutions. For instance, the complete equations of motion of this action is given by this equation, which the linearization of these equations of motion gives some theory, linear theory, with an exotic potential, which is a logarithmic potential of the field. This is in quantum field theory of particle physics. We have ordinary. We have polynomial potentials of the variable, the relevant variable. So here we have a logarithm, and this is a very usual theory, which was found in this paper by Gerasimov and Chatisvili, and they found that in the case where they take the linearization and take p goes to 1, we have precisely this equation. I lack precisely the limit. Under this limit, we have a linear theory and with this potential. And they argue that this theory was related to a theory of string field theory, boundary string field theory, worked out by Witten also in the context of to formulate a theory which was manifestly independent of the background. Well, one way, let me check the time. One thing that we can have here is that P is in general, it's come from P, a prime number. So P is a theory for a Untitled space. So we forget that we come from a non-Archimedean theorem with where P is prime. So one very surprising thing is that in this limit, P goes to 1 is not a prime number. However, this theory has a very interesting connection with another with real string theory. So one problem to understand is why it's possible to take this periodic this prime number goes to 1. So and well, this was done precisely in another paper with Wilson and Miriam, and in this it's possible to see that this has to do with finite extensions of local fields.
Sorry, you have about 5 minutes.
Yes, let me conclude with this. So in the case when we have unramified extensions of local fields, we have that the periodic variables can be changed into another variables p to the a, and it's possible to so the problems of take p goes to 1 is to take e goes to 0. And this can be done if it's possible to take e goes to 0. So there is a notion, a possible notion to take p goes to 1. And this precisely this notion exists in the context of topological zeta functions given by these authors, the Neff and Lesser. They found precisely a rigorous notion to take the limit p goes to 1, taking e goes to 0. So we compute, we repeat the regularization for these unramified extensions of local fields, and we find the regularization of the for this field, these extensions, and we repeat the computation. We find once again the regularization theorem, which we show that is also valid in this case. And now we have the possibility to take a p goes to 1, and in this limit we have I only mentioned one example, the 4-point amplitudes. So we have we compute in general for any e, for any value of e. For this is very easy to compute, and we take finally e goes to 0. And the amplitudes that we call topological zeta functions are for the 4-point amplitudes are precisely these amplitudes. For 4 and for 5 amplitudes, it's also very easy to see, to check the amplitudes. And we check this. Another way to check the physical point of view to check this was to take quantum field theory with this potential and compute the amplitudes in the context of quantum field theory for this theory, and we found that this coincides precisely for the 4 and 5 points with these amplitudes. So this is only for 4 and 5 amplitudes, and we conjecture that this is valid for any amplitude in general. So we give some arguments, but we don't give a rigorous proof. But this is there is another situation in the context with the introducing a B field. We have the Gauss-Alka-1 amplitude, and this was another branch of work done with Wilson and Edgar. So I conclude these two lectures motivated by the study of regularization of amplitudes. We study the periodic amplitudes, which is in some sense more is simpler than the real. Should be the real or complex amplitude. And by considering the string amplitude as the multivariate local set amplitudes in the periodic context, we have found a suitable regularization of this amplitude such that we prove that the conversion of these periodic amplitudes in a certain domain of the momentum space. For P goes to 1, the physical has a physical interest because these amplitudes are connected with real string theory in different ways. We study the amplitudes for extending the periodic amplitudes to with an extended field and take the limit goes to 1 in the context of the local zeta function, topological local zeta function given by the Neff and Lesser. This work was the rigorous part, and the physical, the non-rigorous part was to check that the quantum, the Gerasimov and Chatesville theory has amplitude which coincides for the 4 and 5 amplitudes with this result. And well, this is I don't say nothing about this. I finished the course, and I would like to thank once again the organizers by giving me the opportunity to talk in this school. Thank you very much.
Thank you. Let's thank to the speaker. Are there questions or comments? Okay, let me make a comment. The connections, I mean, the topological set of functions are very deep objects, and the connection between string amplitudes and these objects is very important. Really, here you see a very deep connection between quantum physics and mathematics. Okay, let's thank the speaker again.
Thank you very much.
Thank you, Hugo.
Thank you, Wilson.
Bye bye. See you in Mexico City.
Okay, see you then.
Now we have 10 minutes before the. Now we have. No. Today is different. Today we have only. Okay, today we have only 15 minutes. Because now, today we have two conferences at the end of the day.
con este se habla? ¿Se oye bien?
Vamos a comenzar, ¿eh?
Vamos a comenzar. Manuel, cuando tú digas, me pongo a grabar. Okay, it is a pleasure to introduce to Dr. Christian Garay. He is a young researcher in CONACYT. The title of his presentation is F-rational inflection of hyperelliptic curves, a T and p-adic perspective. Well,
Thank you very much for the invitation, for having me here. I would like to tell a geometric history here today. So first I will speak about the concept of inflection. Inflection, we all know what inflection is. If you have a plane curve, then you look at the intersection of lines with that curve, and some points have higher intersection with lines. And if this happens, you call this an inflection point. Inflection points are controlled by some guys called Wronskians, and if you have some experience with differential equations, Wronskians are just derivations of some functions, and then you take the determinant, and this is a slightly generalization of that concept. So this concept is mostly related to complex and real geometry, but in fact it is possible to formulate it over any field. And in particular, well, first I will send an invitation to what is called enumerative algebraic geometry. Then I will speak about a particular development in this part, which is how do we control inflection for curves which are defined over an arbitrary field, other than the complex numbers or the real numbers. And the curves that we choose to study are very combinatorial. They are called super and hyperelliptic. And it's roughly speaking just a drawing, just a graph. But they are algebra geometric objects. At the end of the talk, I will speak about some valuative aspects of these constructions in which the p-adics and other non-Archimedean fields arise. And just to remind my co-authors or people which is working with me here is Indranil Biswas, Itan Kotteril, Ignacio Drago, Chango Han, and Tony Shaska. And here is a preliminary plan of what I'm expecting to say today. First is a very gentle introduction to enumerative geometry. Then I will talk about inflection, then some polynomials which include inflection, and finally the hardest part, which is valuative things. So if you don't know anything about enumerative algebraic geometry, A very good source for understanding and for starting with this is this paper, but it is not a paper, it is inside a bulletin of the MSRI from 4 years ago. You can just tap this in your browser and it will show up. And it's free, and it is a very nice introduction to what is enumerative algebraic geometry. It is written by Richard Thomas. So what is EAG, enumerative algebraic geometry? Just counting number of solutions to geometric questions over the complex numbers or some other algebraically closed field. If you don't have algebraically closed field, then you may have some problems. We will see which kind of problems later. But when this makes sense, of course, if the quantity of the amount of geometric objects that you want to count is infinite, then this has no sense. So, for example, here are some simple examples. How many lines pass through 2 points in the plane? This is only 1. How many conics? Through 5. This is 1 also. How many lines does a smooth algebraic cubic contains in the space? 27. And how many inflection points does a smooth algebraic curve degree at least 3 in the plane has? So this is also a classical number by Hess. But now these are questions over C. What happens over R? Over R, we start having problems because R is not algebraically closed. So, for example, the first one is still the same, still 1 line through any 2 points in the plane. But the second point is not so easy because some real conics have no points. And this happens when you take a conic with only positive coefficients equals to -1, or just the squares equal to -1, then you find an empty locus of real points. And here things start to get complicated because out of the 27 lines, which was found by Cayley, you may ask how many reals. So these are the possibilities, 3, 7, 15, and 27 by Schlafly. And another refinement for real inflection points of a plane curve are these possibilities where d is the degree. You start with d -2, and then you subtract pairs of numbers until you reach 0 or until this number is positive. So over R, there are several problems because it is not algebraically closed. So you may relax your question. You may not be able to give all the answers, but maybe you may give some upper and lower bounds, or if you are not able to do this, then we are happy with examples. So there is this phrase by R. Thomas, which says that enumerative algebraic geometry has always been about more than just numbers. What does this mean? This means that you can enrich your countings. Instead of just associating a number to each instance of your object, you may associate some other object. For example, you may assign a sign, or you may count more than one object at the same time. And some examples of this philosophy is that if you assign a sign to the lines in the conic, in the cubic, you can classify them in hyperbolic or elliptic. And it is a result by Segre that if you count the number of hyperbolic minus the real number, the number of elliptic, you always find 3. So this is progress because if you want to know how many real lines are in a cubic, there is no closed answer. The answer may be 3, 7, 15, or 27. Contrary to the complex case. In the complex case, you always have 27. But this result tells us that if you count them with multiplicity, then you may construct a constant. And also, this is a topological count made by Klein. So remember that Hess, this is the number of complex points. This is the number of real points, or these are the possibilities for the real points. And then Klein tells you that if you count the number of real inflection points plus twice the number of real bitangents, then this number is always d times d minus 2. So you, yes? Maybe we can discuss that later because I am short on time. Thank you very much for the question. So this is the naive way of doing things because this is only a number plus a sign. But in fact, you can use some heavy machinery called A1 homotopy theory, which is trending now. And instead of assigning a number, you can assign some object, this weird rotten liquid ring. And if you do things correctly, then you can upgrade these sign countings to some homotopy invariants like Cass-Whittaker did here. That reinterpreted these three as some sum of these rotten liquid classes. So the advantage is that signs not always exist in fields, but A1 homotopy theory exists always. So this is a nice generalization of adding a sign for the real case. And one of the main ingredients in this hardcore theory is the Wronskian. And as I said to you, the Wronskian is philosophically what gives you the inflection. So this is the end of the first part. The first part was really gentle because it's just an invitation of this for this kind of problems. Then I'm raising the bar here a little bit because I'm going to talk about inflection, which is not just tangents, which are more tangent to a point in the plane curve, but it generalizes very, it becomes very general. So I will talk about linear algebraic series on algebraic curves, the inflection divisors, and for me, curve will mean smooth projective algebraic for some field, not necessarily the complex, not necessarily the p-adics, not necessarily the reals, any field. So here things start to get some weird. I will pick a curve. So here the story is over the complex numbers. You pick a curve, you pick a line bundle. A line bundle is just a vector bundle of rank 1. So you can think about this as the tangent bundle or the cotangent bundle on a curve. And there is some invariant associated to that guy. It's called the degree. This is the D that lies here. And R, the second one, R is just some dimension of a vector space. So vector space, everyone knows what a vector space is. This is a space of sections of the line bundle over the curve. And you choose a vector subspace of that and the pair consisting of the line bundle together with the vector space. This is called a linear series. This is nothing weird. The most complicated object here is the line bundle, but you can think about it as a tangent bundle if you want. So since we are talking about vector spaces, we can construct some bases for them, and these are finite dimensional. So this guy is well defined, and this weird object is just a section on some line bundle. This is another line bundle. I will explain something about this later, but it is not important. This is just an algebraic operation that you perform on line bundles, and then you take there some particular section, and this section gives you the inflection. So the inflection is just the zeros of this section. And since sections vanish with some multiplicity, this multiplicity is the inflection multiplicity, and then you encode the zeros of this section in a divisor. This is the divisor of inflection of the linear series for the curve. And this way it has a very combinatorial interpretation, because if you take an R plus 1 dimensional vector subspace, and if you pick a point at random of your curve and start looking at the vanishing orders of all the functions in the vector space, then the sequence is almost every time 0, 1, 2, 3, 4, 5, up to R. But there are some special points which do not follow this pattern. For example, there might be a point whose vanishing orders are 0, and then 2, and 3, and 4, 5. Once you find some point like that, you call it inflection point, because it is special with respect to the vanishing orders of the functions here. Here in B. And if you ask how many points, how many special points counted with multiplicity are there, the answer is really easy, because we are over the complex numbers. You just compute the degree of this line bundle, which is r plus 1. R plus 1 is just the dimension of your vector space. D is the degree of your line bundle here. G is the genus of your curve, and everything is computable. So you need to do nothing over the complex numbers. The result of how many special points counted with multiplicity are there in the curve is always the same. But now let's take a closer look at this phenomenon. So imagine that you have your basis. Now it is enumerated. You have function 0 up to function r. Recall that these are linearly independent in the space of holomorphic or meromorphic functions. You take a point on the curve. You take a local uniformizate, a local parameter. That's to say a regular function which vanishes at order 1 here, there. And this is a construction. This is the stock, or the local expression for the stock of the line bundle. Then, as I told you, the Wronskian is just a determinant of some derivations. So start with r plus 1 functions, and then using the derivation map to the Kähler module of differentials, you start taking differentials after differentials, then you take the matrix and you compute the determinant, and that's the Wronskian. This is the name. This is a common name in differential equations when you have when you perform this operation. But if you do this for arbitrary characteristic, for example, characteristic 2, 3, 5, you may find trouble, because derivations, as you know them, they start putting constants in front of the literals. So in order to take away that problem, we change the derivation. And the easiest way to change the derivation to avoid problems in positive characteristic is to use what is called Hash derivative. And the Hash derivative does exactly what you need to do to avoid characteristic, non-zero characteristic problems. So with respect to this derivation, you won't have unwanted zeros once you start taking derivations. And then we use this insight and this definition, and we just change this definition with respect to the classical differential operator, and you just put the Hasse derivative over there. And you go, yes?
There is a typo in the Hasse derivative have R and DJ, the middle of the J. R to J?
Yes, I'm sorry, yes. There is a small typo here. Thank you, Wilson. Here it should be R instead of J. But the definition is really easy. I mean, you can find this definition everywhere. So the insight was, okay, if you want to compute inflection over arbitrary characteristic fields, then change what is problematic to something which may not be problematic, and you just change this for this, and play the same game, and define the Hasse derivation inflection as this guy, no? So this makes sense, and the characteristic of this definition is that you can do this everywhere, and not only on the complex numbers. And I just recall that all this slide is about complex numbers, but now here this is about any field. Now, once again, since in the reals, for example, the reals are not algebraically closed, there may be these kind of problems, which are the possibilities. In the inflection world, you have the same questions. So the question about this problem is, how many F rational. F rational means how many inflection points have coordinates over the phase field. For example, if your base field is R, you may asking how many real inflection points are there in some linear series. And here, this is the question that will interest us. So this is the second part. I already finished, and now here is the most difficult part, because I will look at some particular curves which are combinatorial and some particular bases which are also combinatorial. And I will introduce some guy which is called inflection polynomial. The inflection polynomial is just a polynomial which parameterizes these guys. And here, these combinatorial curves are called hyperelliptic or superelliptic, and I will work over any field. So I just want to mention that this subject is very open. Almost no one is working on this subject, and in particular, non-Archimedean and the p-adic case is still very, very open. So here I have a figure. Let your eyes be attracted to this figure. This figure is exactly a superelliptic curve. So how do you form it? You pick D points. This zero is just there to remind you that this segment is compact. You take D points over there, which are not infinity. Infinity is the infinity point in P1. And then over this, you start blowing up air inside these pockets so that you start seeing bubbles here. How many layers? N layers. So that's a superelliptic curve. It's a generalization of a hyperelliptic curve. This guy is called a hyperelliptic when you just have two layers. So I'm saying here that these guys are combinatorial in the sense that you only need to specify this diopole and the number of sheets. And you magically, if you allow some more restrictions, you can construct this as an algebraic curve with this very simple equation, just adjoining an n root to the polynomial, which is the product of all the constants here. I mean, the polynomial which vanishes exactly in these points. And then you add that this also to be a ramification point of the projection, and that's all. And these curves have the particularity of being combinatorial since they don't depend on the, I mean, they just need some diopole of points here, some number of layers, and then you take this equation, you compactify or you add the point at infinity, and there you go, you have a superelliptic curve. So the simplest example are hyperelliptic curves, and the simple example of a hyperelliptic curve would be an elliptic curve. Just a donut with two balloons somehow, and just two branches or two layers. And what makes this, what makes these curves important from our point of view is that if you take the line bundle induced by L times this mark point, L is some number, for example, 5. You take the line bundle 5 times this mark point and take the whole space of sections, then you find the simplest base possible, which is this one. Just product of monomials in X and Y. Here, X and Y are local coordinates for the curve, such that they follow some archetypical numbering here. So this is called combinatorial because the coefficients are 1 or 0. And each time that you have or you find something which does not depend on the field that you construct, then this tends to be combinatorial because algebra is not appearing or numbers. Anyways, here there is a concrete example, n equals 2, you pick 2g plus 1 points inside the affine line, g at least 1. So this guy is hyperelliptic of genus G, and you take this 2 times OC and then multiply by some positive. And this is the base. Here it is very small, but you just pick 1 x to the square, x to the L minus G minus 1 up to x to the L, and then you stop here. And then you go to the second layer is y to the times x, y times x squared, etc. up to a y x L minus G plus 1 or something like that. And if you have more layers, for example, n equal 4, then you add one more layer here, and it is going to stop somewhere according to these inequalities, which these are polyhedral inequalities. So you add some more layers, which are diminishing in length, but this is a particular case for the smallest number of layers. And away these points, which seem problematic, there is a local parameter, which is x, and if you play this game, if you take the determinant of the Wronskian with respect to x using the Hasse derivative, you find a beautiful functional equation. Recall that this guy is the Wronskian, and the zeros of the Wronskian tells you about the inflection points. So you find this f minus 1 f, which what is f? F is the product of all these roots to some power y. What is y? Y is this variable times some polynomial. So this tells you that the zeros of the Wronskian are the zeros of this polynomial. So these are called inflection polynomials because they control inflection of this particular case, and not only 2 layers, but arbitrary layers and arbitrary ramification over an arbitrary field. So these guys are very general. And in particular, there are some simple ones in which you plug here L equals G plus 1. In this case, the matrix, if you plug here G plus 1, this matrix is a square matrix, but only one y appears. And this gives you a functional equation between the G plus time 4 derivative, Hasse derivative of this function as a polynomial times something else. So let me tell you, the conclusion of this thing is that if you construct this polynomial in some field, you associate this hyperelliptic curve, you construct the combinatorial basis, and this polynomial that appears here can be factorized as the product of x minus the projections of the points every time the point is lying over some point which is not ramified. That's to say, if the projection doesn't fall over x1, x2, or over xt. So this is the definition that we gave. This is the definition as the Wronskian, but theoretically it can be factored as this. So the objective is given this determinantal definition, we should be able to get the factorization. But of course, this is not easy to do. So we are looking for tools to express this polynomial as precisely this kind of product. Here is summarized more or less what I said. The properties of these guys, that the roots parameterize the projection of the rational inflection points. And then, of course, this is a polynomial over f bar because it considers all the inflection points. And the rationality problem is turned into a problem of looking at roots over f, not over f bar. So, for example, for the real case, this would be a polynomial with real coefficients. But we all know that a polynomial with real coefficients may have complex roots, which are not real. And in general, this is what happens. So rationality question that I asked before turns out to be a polynomial question in the quest of roots defined over the field in which I'm interested. Okay. This is only just something that generalized the previous case. The previous case was for n equal 2. This case is for any n. So the same functional equation works now, but the problem is that now we have more guys. We have one for L from 1 over n minus 1. And if n is 2, then 2 minus 1 is just 1, so you forget about this parameter. And m is other parameter. And you have this beautiful functional equation which tells you that some inflection is codified by a polynomial. But more than that, there is a beautiful, so this is a functional equation which gives rise to a discrete dynamical system. Because you can produce the next polynomial in the series, in the sequence, by just plugging this, the previous state of the system. So this is the theorem. These guys, this PML, satisfy that the next one is 1 over n plus 1, the derivation, the Hasse derivative of the previous one times f. Recall that f is the polynomial that defines your curve, plus this u is just the quotient of L divided by n minus m, the previous polynomial times the Hasse derivative of this polynomial. So this also is very open. We don't know what are the characteristics of this dynamical system, but we are very interested in understanding what happens with this. And again, this is not complex. This is defined over any field. Again, these polynomials capture all the inflection points on the curve here, which may lie over points which are not these distinguished d points or infinity. And now I will discuss the last part of the talk. So this is the most technical part. Because I will now introduce a modular parameter. Modular parameter means that it's a parameter that varies over the isomorphism classes of some curves. In this case, this will be elliptic curves or superelliptic curves. And then we are going to see how the polynomial varies when the modular parameter varies. So here we introduce some parameter lambda, and the curve is moving with the parameter lambda. And when you consider the inflection polynomials as polynomials in both x and lambda, then these are no longer one variable polynomials, but they may be multivariate polynomials. In the simplest case, in which lambda is just one parameter, this describes surfaces or curves. This describes curves with one parameter which is natural and the other is modular. And when the characteristic is sufficiently positive, or if it is 0, then we will see that inflection described by these modular families is valuative. So the families in which I will be interested is the Legendre pencil, which you can see here. It is y to the n, x to the a, x minus 1 to the b, x minus lambda to the c. A, b, and c and n are just positive natural numbers. This one is just an element of the field, and lambda is also an element of the field, which moves in the affine line. And the superelliptic Weierstrass is y to the n equals this, and you may remember these expressions from elliptic curves. These are pencils of elliptic curves that I am just changing the 2 by n here.
Here, a singularity.
Yes, but we remove the singularities. We are just looking at what happens at the smooth part. But that's a very good remark. The singularities of these these curves are also interesting, but are very difficult to study. So let me summarize once again what I have done. I pick a field I take care that the characteristic is not n, because if it is n, then there are arithmetical phenomena which are not very pleasant. I pick points on the closure, on the algebraic closure, such that this guy is superelliptic. There are conditions, combinatorial conditions, upon which these two data gives me a curve. Then I said this number, L is in this range, n, I picked n and I left it fixed. And I play a game. I start with a seed, which is P1 U. U is this, time the differential or the Hasse derivative of the polynomial f. The polynomial f is just the product of all the linear factors given by my choosing here the points. And then I play my dynamical system as I introduced it before here. So now this is a combinatorial story, but because I don't need the curve to play the game, I just need the rules. And one thing which is very important is that these guys are defined over the algebraic closure of f adjoining the roots. So this is a minimal field of definition of all these polynomials. So this may be highly computable if I take care of both the field and the root. And the particular case is when this guy is defined over the integers, then all these Hasse inflection polynomials are defined over the integers adjoining an inverse for n. And I will give you, so the evaluative story starts here. So suppose that the characteristic of the field is either 0 or sufficiently positive. I pick the ingredients such that this happens. This is not hard to see. This is just an inequality on 5 numbers. I consider this curve and I compute the polynomial here. And we were able to describe the vertices of the Newton polygon. So the vertices of the Newton polygon this is just a quadrilateral. It has 4 vertices, and it describes a polygon of four sides in the plane. But the important thing here again is that this is valid for any field, such that the characteristic is sufficiently positive or 0. There are no more restrictions here. So this is blind to the choosing of the points. I mean, the Newton polygon is blind to choosing on the points and the parameter of the curve, and also the number of roots that you are taking over the singularities, which are 0, 1, or lambda. I am towards the end. So the second and most important result is about the Weierstrass. The Weierstrass is of this type. We choose these two because for convenience, but also there is a result that also computes the vertices of the Newton polygon, but also the coefficients. So this is the version for the Weierstrass pencil, analog version for the Legendre. And these guys are weird, but they are, in fact, they are not. They look strange and complicated, but once you work them out, these functions are really, really elementary. The only strength notation here is this falling m and these 2 double parentheses. This means double factorials or double falling factorials, in which you start with 3u and you start multiplying by 3u minus 1, 3u minus 2, 3u minus blah, 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 up to 3u minus m. And if you find 2 parentheses, then you take a double step. 2u minus 3 minus 2 times 2u minus 3 minus 5 times up to 2u minus 3 minus twice this integral part minus 1. So these are very natural construction. The coefficients seem strange, but they are not. But what is important is that you can perform a p-adic evaluative analysis on them. So all these expressions are rational, And you may specialize them for other use. And recall here that U is what gives you, this is N divided by L. So N is the number of sheets of your superelliptic curve, and L is the number of how many, the multiplicity of the base point that you are taking the linear series. So this 1/2 means that you are taking L equal to N. But maybe you want to change the U. And the purpose of this slide is to tell you that you can do so, and you can perform a periodic analysis on these coefficients to see how the coefficients of the Newton polygon of this curve change when you perform reduction mod P. And again, this is a family of polytopes. This is a family of polygons which describe the inflection of a modular family of hyperelliptic or superelliptic curves. So this tells you how the inflection changes when you change the parameter. And this tells you that you can perform a periodic evaluative analysis to see how change the geometry of the polytope or the polygon when you factor mod P. And this tells you inflection about the reduction mod P of your curve. So to finish, this is the heaviest slide, and it is just a periodic analysis of these coefficients. It tells you that you can expand the friends that appears on the coefficients of the Newton polygon of the inflectionary curve using very classical theory of Legendre and valuations, periodic valuations. And if you do a case-by-case analysis, starting with the number of ramification points or the number of sheets, you find these expressions in terms of periodic expansions. And so let me spare you the details here because they are not pleasant. They are just formulas. But behind these formulas is the analysis of reduction modulo P of some modular curves which encode inflections of families of this kind of curves. And just to finish, so we hope that this kind of evaluative analysis to shed some light over the inflection varieties when we are working over the periodic case. So far, we haven't attacked the periodic case because it seems difficult. So we started with the integral case and started to see what to expect for the periodic case. So I think that's all. Thank you.
Thank you very much. Alexander speaking. Are there comments or questions? Okay, Christian, could you please comment very briefly why the case in which the curve have singularities is difficult? I mean, this framework? Because from the beginning you said the curve must be smooth. So the singular curves must be difficult.
Yes, so of course, when the curves are singular, in this pencil, for example, or in the other, the inflection concentrates on the singularities, but we don't know how much of the inflection goes towards a singularity. Out of the total inflection, when these guys are smooth, maybe there is, I don't know, 100 points. When you do the analysis over a singular curve, you find like 60, for example. But we don't know how many of the inflection points they generate towards the singular points. And this is a story, for the reals, you have more or less some control over it, but over any other field, we don't know anything about that. And also another thing related to singularities is precisely to understand the singularities of the modular curve. Because the singularities of the modular curve gives you the topology or the circularization of the curve, and it can shed some light on the global behavior of these objects.
Thank you. Are there more comments or questions? So let's thank the speaker again.
Thank you.
Ya lo pagué, ¿verdad? Ya. Sí. Israel, parece que va a intentar conectarse, Mónica, con su iPad. Directamente a... Sí, está mirando. Espera un momentito. A ver si...
¿Aló?
Si le pones aquí en este lado, te están viendo. Voy a ver si puedo mover la cámara. O bueno, mueve la cámara un poco.
Sí, pues, no, todo está controlado realmente. No, pues parece que el chico venía con la enfermedad de Estados Unidos, porque comenzó a presentarse el 23 de mayo. Pero creo que está bien porque otras personas hicieron pruebas y salieron negativas. Sí, sí, no. ¿Y tú estás trabajando en esto ahora de dinámica o eras tu estudiante? Yo no entendí. O sea, tú también trabajas en esto.
Parte de lo que voy a dar es más trabajo de persona. Así que era un poco más sencillo en términos de las cosas técnicas. Más darle un saborcito de lo que pero sí. Manuel, no he visto.
Sí, estaba por aquí, pero se fue.
Es que sé que también está aprovechando para echar unos trámites de la relación. Entonces, a lo mejor tuvo que hacer las fotos.
Ahí que está los resultados con el animador, que está más sentado frente al animador, aparte que es estudiante de es que el otro día le escribí a Manuel Cruz a ver si quería venir a lo de los tacos, hasta que me contestó que dice, ¿verdad? Pues lo voy a considerar el taco, no,
No parece. No, estoy de seguro.
Pero bueno,
Ya está en su casa.
unos cuantos salvadores
Sí, mañana es directo de bachata, ¿te faltaba?
Sí, faltan bueno, mañana nos quedan dos cursos, el curso 6, una conferencia que tuvimos que mover para el final porque y ya y ya terminamos mañana. Sí. No, mañana sí comida.
todavía sobra un cupón, ¿verdad?
Sí, sí, todavía tenemos un cupón. Sí, claro, mañana almorzamos también.
He visto que entonces te vas pero ya al día siguiente.
El día siguiente, sí.
Temprano, ¿no?
De pronto, sabes que me envolví ahí incluso en la tarde, pero bueno, no, lo compré para el miércoles muy temprano.
Esto lo compraste el miércoles a las 6 de la mañana.
Claro. Sí, no, porque tengo que llegar a hacer cosas. Tengo que llegar a hacer arreglos en la casa. Es antes de estar en Estados Unidos, pero tengo que ir a hacer. Sí, me voy a querer, pero no, tengo que, estamos hablando de la casa.
Va a poner la casa bonita porque la quiero vender.
Sí, estamos hablando de la casa, unos carros que también quiero vender.
La carro.
Sí. De hecho, no sé si les interese.
A ver, ¿qué piensas?
No, mira, en serio. Nosotros tenemos un Renault Scala y un Ford, un Nissan Versa. El Renault Scala,
Así de nombre.
no. Lo he tenido por casi 10 años y ha sido muy bueno.
Y si no, ponle las redes que tenías un sensor. No es malo, o sea, no es malo. Y bueno, lo puedo dar por un precio bueno. Lo tendrían que ir allá por él. Se tiene que comprar un Hammer ahí en Texas para que no la aplasten los vecinos. A ver si debo vender esos carros que espera. Una F-150. Me parece que realmente invertirle mucho dinero a los carros no vale la pena. Porque eso se deprecia.
Muchísimo.
Muchísimo, eso se desprecia muchísimo, muchísimo. Lo importante es que sea confiable.
Pues no tenemos cochera, entonces siempre lo dejamos afuera. Le han dado de
Claro, eso le da, sí, eso le pega
y
en
no
cuando
nadie
es
se puede
estación.
decir, "Ay, perdón, están mis datos". Te golpean y
Sí, la gente no le importa. Sí, por eso realmente tener un carro muy fino vas a vivir amargado. Sí, porque lo voltean, uy, ay, no, o sea, a mí ya me pasa así. Mejor no.
si quieres.
Vamos a ir cerrando la puerta. Vamos a ir cerrando.
Vamos a comenzar. It is a pleasure to introduce Dr. Mónica Moreno Rocha. She is a researcher here at CIMAT. Today, she's going to talk about dynamics of rational maps over non-Archimedean fields and bad reduction. Welcome.
Thank you, Wilson, and thank you for being here. I know it's late, and I will try to keep it short and sweet. And you can go home and, well, to the hotel and relax. Thank you for the people that Zoom who's still connected at this time. I was thinking about the title, and I just realized that maybe this over, I should have changed it for a comma instead of. Right, let me know if it's still some echo on the. It shouldn't. Thank you. All right, and obviously, thank you, Wilson, for the invitation to deliver this talk. My work is in dynamics mostly, and I've been doing dynamics of rational maps over the Riemann sphere for a long time. But recently, maybe 7 years ago, I started to get very interested in dynamics over non-Archimedean fields. So this talk is mostly to show you what we do in dynamics, taking some of the tools or non-Archimedean fields into our research. And in particular, I want to talk about bat reduction. So let me start and give you just a quick introduction to what is Archimedean dynamics. I'm going to call it like that. Usually we call it complex dynamics. It's the iteration of rational maps or any holomorphic function over the complex plane or the Riemann sphere. And the nice thing about this is we can do very nice pictures. Once we do into the non-Archimedean, then we lose that part, but it's not too bad. All right, so let me just give you a quick introduction. One of the main ingredients of iterating functions happens to be equicontinuity. If you think about the metric space with some metric, what I denote there as rho, and you consider the family of iterates of a given function that is taking values over the same space, then you know this standard definition of equicontinuity. You take at least defining one point, x. If you have another point that is nearby x, then if they remain close, also their images under any iterate of the function remain close. This is good because what we're going to do is iterate points over and over and over again. And obviously, we would like to know which points remain close on their interaction. If we understand one of those points, then we understand a lot of those points that remain close. So because of that, let me define the Fatou set only using equicontinuity, and it will be just essentially that, the set of points where I know that the family of iterates is equicontinuous. The complement will be the Julia set. Now, Fatou and Julia are the last names of French mathematicians that happened to develop the study of rational maps over the Riemann sphere, and here I will just say the complex projected line, right? In this setting, you can see this is 1920s, that's when probably the biggest boom in the development of rational dynamics happened through the works of Fatou and Julia. So it's almost 100-year-old field. In this setting, equicontinuity is the same as normality. If you remember, a family is normal if any sequence has subsequences that converge uniformly on compact sets, right? So we have the same definitions. Fatou set will be the set of normality, if you want, and the Julia set will be the set where, in terms of dynamics, if you take any 2 points and start iterating, they're going to behave very widely. So we usually say the Julia set concentrates the chaotic behavior of the dynamical system. You see in the picture on the right, what is in black. This is looking at the Riemann sphere. What is in black is the Julia set, and what is in white will be open sets that belong to the Fatou set. Because of the definition, it's easy to see that the Fatou set is going to be open, the other is going to be closed by one is the complement of the other. Repelling periodic points happen to be dense in the Julia set, and attracting periodic points happen to belong to the Fatou set. If you think of what do I mean with repelling periodic, essentially is that locally the function behaves as an expansion for the repelling points, and in the attracting this is just a contraction, right? So you can see that, let's assume there is one fixed point in here, so all the points under iteration are mapped into that region, and these other small disks, topological disks, eventually map into that. There is another component in here. Possibly there is also another fixed point that attracts the dynamics of every other point that lies in there, and there may be some components that eventually map in here, right? And whatever is in the complement of taking all these open sets, that's what you call the Julia set. There is a couple of more properties, as you can see. The Julia set in this setting is never empty. You can prove there is always a repelling point, or something that we call also a weakly repelling periodic point for any rational function of, I didn't mention, but the degree of this rational function should be larger or equal than 2. If you have one of those, the Julia set is never empty. But the Fatou set may be. You can think about this picture that I have in here, like the white regions approaching or closing up and then giving you back the whole Riemann sphere as the Julia set. That can happen. And there is two other properties that I'm just writing it for the Julia set. They also hold true for the Fatou set because one is the complement of the other one. One thing is that they're invariant, that's the second to last condition, and also that the definitions of Julia set or Fatou sets behave nicely under iteration. If you look at the Julia set of the n iterate of the function, that's exactly the same set as the Julia set for the rational map. So this is a quick idea of what is the Julia and Fatou set for rational maps. I should mention two couple of theorems that I will contrast what happens in non-Archimedean dynamics. The first one is due to Dennis Sullivan. If you are hear the news, he won the Abel Prize recently. And in the 1980s, he proved that this conjecture it was called as the wandering domain conjecture. He proved that if you have any rational function of degree 2 acting over the Riemann sphere, then any Fatou component eventually becomes periodic. There is no wandering components bouncing around in the Riemann sphere. And that was a big question that was from the time of Fatou. It remained open until the 1980s. He solved this conjecture. There is another one. Once you know that every component is periodic or eventually periodic, then you can study the dynamics when you restrict just the iterates of the function to that component, right? So as we mentioned, let's assume that I have one component that is k periodic. Then I can look at the sequence of nk iterates of that function. From the definition, I know that's normal. So I would like to know what is the limit functions of those sequences that converge uniformly on complex sets. So very quickly, I can tell you that if the limit functions happen to be constant, then you are in the case of what we call attracting domains, right? What you see here in this picture that I just circled, the black curve is the Julia set. Everything that lies outside are points that escape to infinity on their iteration. And what you see in blue is the orbit of one single point that is being converged into some fixed point. Okay? So in that sense, those are attractive. The one thing that I have on the right is a rotation domain. If the limit functions are not constant, then usually not usually, you always get a rotation domain. The exterior boundary that is in here, almost, is the Julia set. Everything outside escapes towards infinity on the iteration. And if you can see several curves that define a foliation. If you take any point in that one of those curves and start iterating, the orbit becomes dense. The iterations becomes dense in that curve. So you can think about a irrational rotation. In fact, what you can prove is that the dynamics of the function in this particular type of components is conjugated to irrational rotation. And one thing that I want to point out is that irrational rotations are injective, right? That's going to be important for what I'm going to tell you in a moment for non-Archimedean dynamics. Okay, so that's essentially a very quick introduction to dynamics over the complex plane. And now let me tell you what we can do when we change the field. Instead of working with C, let's go to just more general fields. And let me start with this. The same role that Julia and Fatou and Montel played for rational dynamics is now played by these people, Sibelman, Benedetto, and Ribera-Letelier. They pretty much gave us the basics of the field. It was mostly defined over CP, but then eventually was generalized to other fields, right? So I need to tell you a little bit about non-Archimedean fields. I know that you have seen it in several contexts, in particular also with Rogelio Perez talk. He did mention a little bit about this. I won't go into much detail, just to give you the flavor of what I'm trying to explain. So let's start with the field. Most of the times I will be thinking about complete fields and algebraically closed. So we get rid of QP and start CP and any other field that you like. And we have this property, non-Archimedean property of the absolute value. We define the projected line over K the same way that you do it for the complex plane, right? You identify the plane, the field union infinity, and by considering just the homogeneous coordinates. You can also describe the projected line over K as this union in terms of the homogeneous coordinates. So essentially you are gluing together two copies of the field, right? You have the valuation ring, you have the maximal ideal, and then you define the residue field by this quotient. This is important because now in this case we can take reduction, which when we do complex dynamics, we don't have that tool per se, right? But here we have it, and that's going to be very important for the dynamics later on. So as I said, in general, I'm going to be working with mostly complete and algebraically closed fields. Let's start. I mean, let me define then a rational function given with coefficients over the field. I'm always going to start work with degree 2 or higher, That's where the dynamics becomes really interesting. And since I give you the definition of Julia and Fatou sets in terms of equicontinuity, it's the same definition here. It doesn't matter, right? So once again, the Julia set is going to be the complement of the Fatou set, while the Fatou set in this case is the union of open sets in the projective line of K, where you have equicontinuity in the sets, right? All right. Now, I cannot talk about closed open in the sense, topological sense that I mentioned before. The Fatou set was open for dynamics over the real, over the complex line, projected line. And in this case, I cannot say that. But essentially, what we still have is that repelling periodic points belong to the Julia set. And what we call non-repelling periodic points, which includes the attracting ones, are also in the Fatou set. There is another type of periodic points where that locally they don't behave like an expansion or a contraction, but as an isometry. Those are also included in this part here. Anyway, if I know something about periodic points, I can tell you which ones belong to the Julia set or the Fatou set, which is nice. I still have the two other propositions of invariance of the Julia set and behaving nicely with iterates. But something that is really the first thing that any dynamicist is surprised by is this condition. In the previous case, the Julia set was not empty, while the Fatou set could be empty. This is completely reverse. The Julia set, the Fatou set, sorry, I'm so used to saying it that sometimes I still get it wrong. In this case, the Fatou set is never empty, and the Julia set may be empty. And that has to do with reduction. Whether the Julia set is empty or not has to do with reduction. So here's a theorem by Morton and Silverman that says that for any rational map, I forgot to say degree at least 2, if it has good reduction, then the Julia set is going to be empty. Essentially what happens is that if the rational map has good reduction, it satisfies a Lipschitz condition, so it doesn't expand the metric. So then everything is contained in the Fatou set, where you know that it's equicontinuous, right? That's essentially the idea of the proof. And reduction, I will talk a little bit more about reduction, but here's a definition of how to reduce a rational map in terms of their components F1 and F2. And the degree. Obviously, this is if you have seen this, this is the standard definition of good reduction. Anyway, so Julia set could be empty, and that has to do with good reduction. So for dynamicists, we prefer bad reduction. Bad is good, right? And let me tell you about the other two terms that I mentioned, the one from Sullivan that is wandering domains. There is no wandering domains in the case of complex dynamics. Here you can prove, and that was Benedetto's result in, I think it was after his thesis, but he proved that there exist polynomials of degree at least 3 that have wandering domains. So there is some other conditions you can add to the field where, and to the functions where you can be sure that there will be no wandering domains, but in general, it's not true. And also there is, I mentioned the classification of Fatou components. There are essentially 2 in terms of the limit functions, attracting or rotational domains. Here you have something very similar, and I don't want to get into the details because I don't need to for this talk, but you also have attracting and something that is called indifferent components. And in there, what you have is injectivity. So as you had it for rotation domains, where things are conjugated to an irrational rotation, what it remains true is that at least the rational function restricted in this case, in this scenario, to an indifferent component becomes injective. All right, and I just mentioned quickly a couple of results, which in the abstract, I did mention that I wanted to talk about this part, but I just realized it becomes too technical and it's late, and you probably don't want me to keep going and going. So I'm just going to mention this. Not only Rivera-Letelier proved the existence of these 2 types of attracting or indifferent domains, he also provided examples. And the examples that were known at the time were for those rational functions with good reduction. What I did with Victor Nopal, and he has been here in the conference, my PhD student, we built examples where rational maps with bad reduction also have this type of indifferent domains. And there's this, I like this result. I don't know if he's around on Zoom or something, but he has a recent result that he can prove the existence of wandering domains for quadratic rational maps. It was known for degree 3 polynomials, but he can lower the degree and show that for degree 2 rational maps, which is, I think, a very nice result. All right, so let me go back to dynamics. Dynamics over the complex plane, over the Riemann sphere, or the projecting line, over the Riemann, over the complex values. And let me tell you about a problem that dynamicists deal with that recently was solved using non-Archimedean techniques. So I'm going to talk about the boundary of the rational functions of degree D with coefficients over the complex numbers. So let's start. Let me tell you what do I mean with the boundary. I can start with D larger or equal to 1. Eventually, I will go degree at least 2. But if you define rad D as a collection of those rational functions of the same degree on complex coefficients, you can identify that as an Zariski open set of the projected P to 2D plus 1 space. And essentially what you do is an inclusion. You take the rational map, A0 and B0 are not 0, and you just essentially do the projection with looking at the homogeneous coordinates, right? So we're going to define the boundary of the rational maps of degree D as this difference. You take P to D plus 1 and take this open Zariski set. And whatever remains, that's what we're going to call the boundary. So essentially what is happening in the boundary is when you lower the degree of the rational map. And I'll show you an example in a minute. So another technique that we use a lot in complex dynamics is that we work with one-dimensional families of holomorphic functions, in this case, rational functions. You take a parameter, you take first, an open neighborhood of the origin, and then you parameterize a family of rational maps with T taking values over U, right? And the only thing that we do is that for each element T in U, you get a rational function. And you want it to be exactly of the degree D. You don't want it to get it into the boundary. That's what we call the holomorphic family. But in the case, and this is obviously a definition, so in the case when T equals 0, the rational function that you get lowers the degree. So it's in the boundary, okay? And that's what we're going to call a degenerated family of rational functions. Okay, so we have a parameterized family. We want to study what happens to the dynamics of degenerated families. And I'll show you an example. Yes? Say that again? It's when T equals 0. That's what I call. Yes. So when the parameter is 0, I'm going to define it as that point, that function lowers the degree, so lies in the boundary. It can be done obviously in any other value, but it's good for what we're going to explain. So let's say that when T equals 0, that rational function is no longer of degree D. All right, so I'll give you an example. This is taken from a presentation of Xavier Bouffe. So just, I decided to present this because it's quite easy to see. It's not too involved. So you start with this family of cubic functions, rational functions, where, as you see, as T goes to 0, you hit the boundary of the rational, you lower the degree, right, from 3 to 2. All right, what you see in the pictures, the one on the left is the Julia set, the one on the right is just a zoom down to the center of the Julia set. It's a dynamical plane, I should say. Everything that lies outside that is black maps through iteration to infinity. Now, you can see that this rational function has a pole, simple pole at the origin. So right here at the center is the origin. If you want here, this is 0. So this whole black region maps 1-to-1 to the exterior, and then points escape to infinity. Everything that you see in black eventually escapes towards infinity, eventually mapped into this region, and that one maps away, right? What you see in white is also Fatou components. There is a 2-cycle of these 2 components, and everything that lies in these regions are trapped by those 2 cycles. And there is here 1 cycle, but it doesn't matter. What you see in white is also Fatou. So what is the boundary between the black and the white is the Julia set, okay? And what we're going to see, this is for some given parameter t that is small, positive and small. And what I'm going to show you is when t goes to 0, what happens to the picture. So we start with this. Here is t is smaller than the previous one. The same ideas, the black, the white, Fatou, the boundary in between is the Julia set. And you can see that this component that contains the pole is starting to shrink. Not only that, the same goes for the others, right? As you move along, you see the same. Everything is, there is this 2 cycle and this point that remain the same. The dynamics don't change. It's just the structure that you see. There is one more before pinching out the things. So we don't like this. When t goes to 0, this is the dynamical plane of c². Everything in here obviously converges to 0 under c², if it's inside the unit circle, and everything outside escapes towards infinity. And obviously here there's nothing, right? It's more like a joke that I put that picture in. So dynamically speaking, I don't like this because I lose the information from this picture to the next. So how do I figure it out? Well, is there a way to keep going and have some structure that I don't see here because everything is being attracted to the origin, or not? Maybe I'm hopeless, and once I reach the boundary, that's it. There's nothing I can do. Unfortunately, we can say something. And the technique is through rescaling limits. There's other techniques, but I'm going to explain this because it's obviously related to non-Archimedean fields. So let's start with a degenerated family of functions. Now I'm going to start with degree at least 2. And I'm going to also consider a family, holomorphic family. There is 1 parameter here, and each element is a Mobius transformation. I'm going to say that those collections of Mobius transformations is a rescaling if I can find several things. 2 integers, 1 function that is a rational map of degree d prime, and some finite set that we'll discuss later, such that if I do this composition of the L iterate of f and compose with the Mobius transformations, this is essentially a change variable, then as t goes to 0, converges to this function, which makes sense because what I'm saying is I'm lowering the degree, right? Obviously, what I would like to do is to have something that is meaningful, that is not necessarily in the example that I'm explaining C². So whenever I can do this, I'm going to say that G is a rescaling limit of the family, okay? This is the most important part of all this slide. All right, so let's go back to the example. And let's seriously perform some magic. At least that's what I when I started for the first time. Once again, I have this family, cubic rational maps, and this is the algebraic limit as t goes to 0, right? I'm going to just, essentially, this is a Mobius transformation multiplied by a cubic root of t, c, the value of c. And then, oh, sorry, this should be set, not t. I realized I made a mistake here. This should be c, mu times c. So I do that, I do the composition, and essentially what I get is this new rational map. It's not good enough because as t goes to 0, everything goes away, so I don't like that. So if I do the second composition of this, I obtain this expression. And this is very nice because this one essentially goes to 0, but this remains in the computation. This is what we call a rescaling limit of that family. What information is that G giving me? Is really giving me something, or is just something that came up from this computation? Well, there is some nice structure in terms of the Julia set. What you see on the right, on the left, is the picture that I had before when T was really small. There is the pole and the components of the pole, etc. Right? And this is the dynamical plane of G. This is also a picture by Xavier Bouffe. I did my own computations, and I have so many errors that I couldn't distinguish between this picture and this picture. So I'd rather show you this. What you see now in yellow is the Fatou set, and in black is the Julia set. And structurally speaking, I mean, in terms of the geometry, it seems that should be the limit instead of obtaining C squared, right? So I should say I should be careful because the dynamics is not the same. Now everything in the yellow parts converges to the central point. Here I have these 2 cycles and 1 cycle in it. So it gives me some information, but it's not a complete information in terms of the dynamics. But there is some information that I definitely prefer than what I had before. All right, so this is nice. How do I get rescaling limits? How do I get G? How do I know even there exists a rescaling limit? And that's when non-Archimedean dynamics comes into play. So here's the main ingredients of what I'm going to be talking about. Reduction essentially is over non-Archimedean fields will help us to understand the rescaling. This tool that I don't have in complex dynamics, when I look at this same problem from the non-Archimedean point of view, does help me to connect the dynamics of G with the dynamics of the holomorphic family. So here's essentially the main ingredients. You have a family, let's assume degenerated, it doesn't have to be. Take a family of rational maps of the same degree, and you can think, since this depends holomorphically on the parameter T, then also the coefficients of the function depend holomorphically on that. So I'm writing this as holomorphic functions, Taylor series, defining some neighborhood of the origin. The neighborhoods may differ, but I can find like a common neighborhood for all the coefficients. Therefore, I can think about this function is actually as having coefficients on the completion field of formal Puiseux series, which is, as you know, algebraically close, right? And if I do that, then I can identify the whole family of rational maps with a single rational function that acts on, which I have it here, acts on the projective line of L, and study the dynamics of that function. And that dynamics will eventually bring me back to the function G. So let me just very quickly, I don't know if you have seen this in other talks, but we don't need to do with much details this type of presentation. So let's start with a point C and L. You can write it as power series, where now the coefficients take values over the over Q, and the coefficients are also AG are complex numbers, right? You define the absolute value by this expression, and we have this condition that if I have one of those elements in L that has norm 1, if and only if, and let me do the symbol of quotes, it does not vanish at T0. There is a constant coefficient in the expression that I have for C. We have the valuation ring as before, the maximum ideal, and the residue field. And something very nice, very special of this field L is that the residue field can be identified with the complex numbers. And that's going to help me to make the connection with back to rational dynamics. You can do as before, identify the projection, the projectivization of L by the standard homogeneous coordinates, right? So let me just move and then define reduction. How do we define reduction here? Well, I'm going to define it as a map that is acting on the projective line of L to taking values of the projective line of C. And essentially, you take the quotient that you already have, and remember that I can identify the residue field with a complex number. So then this one is nicely embedded in the projective line. And any other point that lies in the complement, I just send it to infinity with this map. And that's the extension of the reduction over the projective line over L. Now we have a rational map. I can write it in this form. I take polynomials that now take values on the valuation ring, take the reductions denoted by this, and I'm already thinking that the coefficients lie already in C, because I have this identification. And also I need to be careful because these reductions may have a common term, which I'm going to call H. If I factor that out, then this is going to be the reduction of the rational map, just R over S, and I decide to define it as infinity if S equals 0, right? So as long as you don't have a C value in the zeros of this common component, and the map is not constant, then I have sort of like a diagram that commutes, right? The dynamics of the rational function acting of the projective line of L commutes on the reduction with the dynamics of its reduction acting on the projective line over C, right? I need some conditions, but if that is possible, then it's nice. I can pass from one dynamics to the other. And here's the lemma, is just connects the first part of what we have. Essentially, a family of rational functions can be identified with this particular function that I told you is just representing the whole family of rational maps as a unique rational function acting with coefficients over the projective line of L, right? If you do that, then as t goes to 0, what we see is this behavior. The rational family converges to the reduction of this function. And here the reduction, I see it as taking values over the complex, acting on the complex projective line, right? And the points that I had to take out that I mentioned before is just going to be the zeros of the common factor of the reduction. So in terms of the example, I'm not saying much. I have this family. I can define f of t essentially as the same family as seeing it. The coefficients I'm seeing as elements in PL. And what happens is when I do the limit, when t goes to 0, the reduction is essentially that map. When is that conversion? Where is that conversion? Outside the common 0 that has these two polynomials. That's essentially what this lemma says for the example, right? Not much, but it's not telling me what is G. That's the problem. Okay, so let's talk about that. And essentially, we have to go to another space. We have to go to the Berkovich projective line over L and look at the dynamics of big F in order to find G. I won't give you much details, but just the basics of the Berkovich projective line. In terms of base space field is L. This is going to be a topological space. It's compact, it's Hausdorff, it's R-connected, tree-like, and has PL1 as a dense subset, which is nice. I mean, for those that we do dynamics, being compact and arcwise connected is wonderful. We can think almost like what we think for iteration over the Riemann sphere, right? It's almost like that. There is a way to define an arc that connects any two distinct points on the Berkovich projective line. And there is also this equivalence class. If I have, let's say, a point X, I can connect with a point Y. But if this line has an arc for G prime, then I say that Y and Y prime are related. We'll see in a moment a nicer picture. So I can also define the tangent in terms of a given point of the Berkovich projective line, and that will be the collection of equivalent classes that I just defined. You give me a point, find all the equivalent classes that you have, those that arcs that are shared initial part, and that's what we're going to call directions or vectors of the tangent plane. Anyway, so you probably have here that the Berkovich projectile lines have 4 types of points. I'm just going to consider points of type 1, which the cardinality, there is only one direction, only one vector, if you want, in the tangent space of the point. This is, I denote by this, the cardinality. If it's 1, then we say that X is a point of type 1. So for example, this point in here has a single direction. That will be a point of type 1. If it has 3 or more directions, like this point in here, the Gauss point, actually, if it has 3 or more, it has infinitely many, uncountably many directions, and those we call it type 2. There is also type 3 and type 4. Type 3 will be a point that has only 2 directions, and type 4 will be kind of like accumulation points of all these structures that you see here. But what is important is essentially type 1 and type 2 points. Okay, so we do dynamics over this projectile line. By the way, this is just one part of the projectile line. You will have to add another copy here to obtain the projectivization of the Berkovich projectile line. Anyway, so here's the pretty much the last part of the talk. You can prove that if you take the Gauss point, which is a type 2 point that's quite special in the Berkovich projectile line, if you take the tangent space of that point, that happens to be identified with exactly the projective line over C, which is great. And I'll show you why. I won't go into details. There is other proof by Rivera-Letelier that says that if you have now rational maps acting in this space and happens to have to fix the Gauss point, then here's the information that we were missing. The degree of the reduction of that function comes from the local degree. I won't give you the details, but essentially it's the cardinality of the solutions near the Gauss point of phi. And the tangent space at the Gauss point, sorry, not the tangent space, the tangent map defined over the Gauss point is exactly the reduction we were looking for. So if we translate that into the family of functions, rescalings, then we finally get the function G. Here's the first part is essentially stating that you have a family of rational maps that have a rescaling limit with M and G and all that, right? This particular iterate and so on and so forth. If you have that if and only if, the function that I define from the family, which is this F, iterated to the L power, has a fixed point that happens to be the image of the Gauss point by a Mobius transformation that is acting on the Berkovich projectile line. The degree of that map, local degree, is exactly the degree of G, which I'm looking for. And the best part is that the tangent map defined over that point is Mobius conjugate, or if you want, isomorphic, and with an isomorphism of the projectile line over C to G. So this is essentially giving me what is going to be the rescale limit for G. The proof is not that hard once you have all the information that I mentioned before, but you can put it back together and obtain this if and only if condition. So let me just finish by saying that, first of all, rescaling limits of a family of rational functions do correspond to periodic points of some map that I can represent the whole family as a single map, but now it's acting on this Berkovich projectile line. And I'll be interested in the periodic points, and some of them will be rescaling limits. There is at least one rescaling limit. So Kiwi has proved that it's not only one. There are examples where you can have infinitely many distinct rescaling limits. So there is more things that are open. How to distinguish this? What is the conditions that will give me at least one rescaling limit or infinitely many there are many other questions. So I'll give you some of the references. In particular, this last part was based on the paper by Jan Kiwi in 2015, and the last three are, well, related to dynamics, non-Archimedean dynamics. Thank you for your attention.
Thank you very much. Are there questions or comments? Lynn, I have, no. Oh, I'm sorry.
Okay. Okay. Would be that possible to do the same with other algebraically closed fields instead of taking the complex, taking CP or any other complex algebraically closed field?
Algebraically closed, yes, you can do that. I mean, what we did in this particular case is that when you work with a family of rational maps, you can go back to obtaining some information because of these identifications that I had with the projective line, the Berkovich projective line, and so on and so forth. But you don't need to do that. I mean, if that's not what you're trying to go back to the complex dynamics, then you can keep working on more general fields, definitely. That's not a restriction.
Thank you.
Are there more questions? I have, oh, sorry. A curiosity about the field L. In algebraic geometry, there is a field called the Puiseux field. Is the same field? The L field, in the construction, somewhere in your slide, you introduce the L field, which is a field consisting of power series, formal power series. But, okay, go back one. Oh, the Puiseux, exactly. Okay,
yeah,
I didn't see that.
Excuse my French.
No, yeah.
Pronunciation.
Yes, this is the
But yes,
yes,
I think it's the same that you're thinking.
Perfect.
Yeah.
Now, a curiosity, in the case of the p-adic numbers, are there visualizations, the Fatou and Julia set for some mappings?
Not that I know, but I can tell you that when my student, Victor Nopal, was working with rational maps, at the beginning, it was only on CP, and he was able to figure out a visualization of how things are working in terms of the disks.
But I'm talking about computer visualization,
no,
the one that you presented at the beginning of your talk.
That I haven't seen. I would be happy to see it.
Okay.
But this representation that I was mentioned from Victor, it makes a lot of sense. It's just that they're not computer generated. But I haven't seen any computer generation, but there may be some, but I don't know them.
Thank you. Are there more questions or comments? So let's thank the speaker again.
Thank you.
Okay, so see you tomorrow at 9:30. Déjame decirte que hay construcciones de destacamientos de los teóricos de los complejos. Existen teoremas. Entonces, los teoremas podrías